Hi, everyone. We're going to start our Optimizing Human Learning workshop. So thank you all for coming for this workshop. So this is a workshop co-located with AI Ed, organized with by myself and Atinria and Benoît Chauffin and Fabrice Popino from Central Supélec and LRI, and Hisashi Kashima from Kyoto University. So we're gonna get started soon. But first, here are a few introduction, some slides in order to understand what we are talking about. So we will start with these 30 minutes where we will introduce some concepts. And then we will have an invited talk by Usha McKay from the University of Edinburgh about teaching categories to human learners with visual explanations. And after that, we'll have an accepted paper about non-compensatory knowledge tracing with local variational approximation by Hiroshi Tamada from NEC. And after that, we'll have a 15 minutes break. And we will then continue with another invited talk from Jill-Jênn from the University of Chicago about teaching multiple concepts to a forgetful learner. And then we'll have an accepted paper by Fu-Hua Lin from Athabasca University in Canada about adaptive quiz generation using Tom sound sampling. And after then, there will be another 15 minutes of break and an open discussion where everyone will be welcome to discuss, and we will open the microphones. But first, so what I want to insist about is the fact that you are feel free to ask questions in the shared notes. So for those viewing on YouTube, maybe you will mention some questions in the chat, but mainly here we have the attendance from AI Ed, who can just use the shared notes in the left column, where you can add your name with your question, and we will read it for you to the presenter. So all talks will be 20 minutes long, and we'll have 10 minutes of questions, up to 10 minutes, during which we will read your questions to the presenter, and we may also open mics if we have time for that. So we are talking basically about optimizing human learning, and I want to just give a few, take advantage of the time to introduce a few concepts. So when we talk about optimizing human learning, it's related to many fields in educational data mining or machine learning and education. So mainly we can talk about student learning and forgetting models. So the fact that over time, your student may attempt several times some exercises, and they may forget what they learned. And you mainly want to predict this, like to have some model in order to predict what will happen in the future. And the second talk will mention one of these student models. And when we have this kind of student models, we can do some adaptive learning. So we can learn a policy to ask questions to students. So there we will have the talks number 3 and 4 that will talk about it, from Jill-Jênn and Oscar Lin. And this is also related to spaced repetition, when you have this kind of flashcard-based systems like Anki that you use in order to memorize some kanji, for example, or concepts, for which you also want to design some clever scheduling algorithm, so adaptive scheduling, that may require or not a student model. Or also, it's also related to the fact that you may want to select a set of examples in order to teach a concept. So it's kind of related to curriculum learning, where you would want to know what is the best sequence of exercises to show to a student to make them learn a concept. And also to machine teaching, which is more theoretical part in machine learning, where you still want to know what is the effect of sample on learning, of which can be the learning of machines or of humans. So I will give briefly a really simple example of student learning model. So it's in item response theory, you can have a rash model where when you observe student data of students who attempted items in the past, then you can estimate automatically the difficulty of items. So this is some kind of prior knowledge that can be useful in order to predict whether an exercise will be too easy or too difficult. So here you have on the y-axis the probability of success of an exercise, and on the x-axis you have the level of a learner. So for example, if you have and so you have the yellow curve that represents a skill that you would like the difficulty of an item, but here we would assume that an item only requires one skill that is of level 3. So if you have a learner who is of level 5, then they would have a high probability to get correct an item of level 3. So this is why you would have like 88% probability to get this level 3 item correct, but they would have only 50% chance to get correct an item of level 5. So which is a blue curve. So that's what we can learn directly from data. You can actually try to learn where are these curves located in what you are trying to assess from the student. So then, given the curves, we can get some likelihood about what could be the level of the student, and we can refine adaptively this. So what do I mean by this is, if let's assume you can order all exercises by difficulty. So let's say question 1 is the easiest one and question 14 is the hardest one. Then if you have this kind of really simple student model that can learn how a student would behave, so the curves we saw before, then we can adaptively ask a question, let's say ask question 5 first, and if the student gets it correctly or not, you can decide what question you will ask next. So that's why, like here, you would have Alice, both Alice and Bob who would get correct the first question, and so they will be routed to question 12, which is a harder question. And then Alice will get it correct while Bob will not get it correct. So that's how the difficulty of the test might change over time. So this is why if you have a student model of what is happening, like how the student is learning or forgetting, then you can decide how to present items to students. And there are other, of course, there are many models, student models, and you can, for example, say that tasks may require not only one skill that would be of some difficulty, but multiple skills, which makes it more challenging. So here is a toy example where you have 4 tasks that require several skills. So for example, sending a mail, like you would have here you would have as rows the different items or tasks, and as the columns, you would have the different skills or knowledge components. So for example, the fact that someone knows how to use a form or knows what is a mail, and so you would require both of these in order to, the mastery of both of these concepts in order to solve correctly the task of sending a mail. So if I can have this kind of expert-defined or directly learned from data matrix drawing the link between items and skills, then I can do something clever with the way I personalize my system. So, and here to give you an example, so if I first ask the fact of sending a mail, and if my user gets it correct, then it means that presumably they will master forms and mails, so I don't need to So if they fail at this, I don't need to ask the final question, which is enter a new URL, because as the student already failed that form, then they may not solve this exercise. It may be too out of reach for them. So then I can decide whether I would better ask the second item or the third item, but then I don't need to know whether they can fill a form or not, and then I can just another item from which I will learn information about other skills. And these systems can be compensatory or non-compensatory, which means either like one of the skills is enough to solve the item, or you would need all of them to be correct in order to. So I'm gonna let Benoit speak if he can open his microphone.
Yes, maybe JJ, can you give me the
yes.
hand on the, if possible?
Yes, here you are.
Yeah. Oh, thanks, great. So hi everyone, so my name is Benoit Chauffin and I'm a PhD student in the Laboratoire de Recherche Informatique in France. And so I'm one of the organizers of this workshop. And so what I want to talk to you about right now is, so we saw with JJ how we could adaptively select the next item to ask the student so as to make the student, so as to converge with the correct knowledge about his or her knowledge state actually, which is called cognitive diagnosis. But what we can also want to do is to improve the way humans learn, not only assess, and especially we can want to optimize and improve human long-term memory with, for example, the help of adaptive spacing algorithms. So adaptive spacing algorithms basically rely on two major robust learning strategies that were discovered by cognitive scientists, which are spaced repetition and self-testing. So spaced repetition consists in temporally distributing learning sessions of a given piece of knowledge instead of spending the same time, but in a single big massed session. And on the other side, self-testing consists in testing one's knowledge after learning instead of simply reading the same lesson again. So basically, you can just like try to make some free recall about the knowledge you've learned, or maybe you have some kind of quiz already prepared. So anyway, all of these types of self-testing help students and human memorization. So both of these learning strategies, so self-testing and spaced repetition, have been shown to improve memory retention on large learner populations. But such recommendations from the cognitive science literature are yield generic and one-size-fits-all reviewing schedules. So basically, you would have some kind of strategy, such as reviewing when you are about to reviewing, for example, 2 days after learning for the first time your item. But this is just like the same fixed schedule for everyone. The idea of adaptive spacing algorithms is to do better than that and build upon these works by adapting the spacing between two reviews of the same piece of knowledge based on the learner's needs. And usually we infer this type of learner's needs from the performance history of the user. And that way, we can provide students with adaptive and personalized spacing schedules. And several experiments have shown that compared to fixed reviewing schedules, such adaptive and personalized spacing schedulers would yield increased memory retention over time. And so this is what this picture represents. So we have this student Alice, not the same Alice as before, but so she wants to learn two skills. So skill 1 in orange and skill 2 in green. So you have on the x-axis you have the time t. And so what would an adaptive spacing scheduler do is that, for example, skill 1 here, so Alice fails because there is a cross, fails to remember this skill or this item, and so the adaptive spacing scheduler manages to find that there is a problem here and that this item should be presented to Alice sooner than they previously thought. And the second time it's also incorrect. And so the time gap between the two next repetitions, so here, is shorter than here. So because we assume that the scheduler has found that Alice should review it even sooner. But here, so the answer is correct. So the next time it's very much later, and here we see that Alice manages to remember correctly, thanks to the repetitions, this item. And so on the contrary, we have this skill too. So the first acquisition is here, and we see that here, so Alice manages to remember correctly this item. And so so this may come from a real good mastery of this item, or maybe just luck. So to test that, the adaptive spacing algorithm will let some time pass, and here present this item, make Alice review this item or self-test her on this item at this time. But here she fails to remember it. So then there is a second repetition here, and she finds the correct answer. And so this is the basic sketch of how adaptive spacing algorithms work. But you have very different varieties, of such algorithms. You have handmade heuristics, data-driven policies, and other types of policies, for example, based on student models and stuff. And so here, I just give you a small example of the way the Lightener system works. So the Lightener system is one of the long-standing, one of the oldest adaptive spacing algorithms. And here, it works with flashcards. These are flashcards, for example, that are used with the platform Anki. And these cards are used to periodically review simple pieces of knowledge, such as, for example, vocabulary or historical dates. And on one side of the card, there is a question. And on the other side of the card, you have the answer, and which you want to make the learner review. So you will ask the first side of the flashcard to the learner, and then if he or she answers correctly, you will have different schedules afterwards. And so the Lightener system uses this set of boxes, and each number on each box indicates the frequency at which cards in this box are reviewed. So in box 1, it's reviewed every day, in box 2, every 2 days, etc. And if a learner, in the basic form of this algorithm, if a learner manages to recall an item, a flashcard, at any timestamp, so from the date he has to review at this timestamp, then the flashcard is put in the next box, which is less frequently reviewed. For example, on the every 4 days. But if he fails to remember or recall this flashcard, then the flashcard is put in the first box, which is reviewed every day. And so we see that this is one of the simplest spacing algorithms to optimize human memory, and it dates from the 1970s. But we can already see that this type of algorithm adapts to the learner's performance, because the review frequency of a flashcard directly depends on how well the learner manages to recall this flashcard. So this is very basic form of adaptive spacing algorithms. Of course, you have other types of such algorithms that rely, for example, on student predictive models to select the best flashcard to review at any timestamp. For this, you have to be able to model, to infer how well a student will be able to recall a given flashcard in the future based on the past performance. And so, for example, this is the case for Lindsay et al. With one of their papers, and also from Yusin's work, who will present this work in the third talk about teaching multiple concepts to forgetful learners. And so this leads us to our final point here, because I've been talking to you about student models and adaptivity, but we do not necessarily have to assume an underlying student model to perform such type of adaptivity for improving human learning. So this is so for example, this is the opposition between model-based and model-free reinforcement learning. And all in all, we do not have to necessarily rely on an explicit student model. We can rather define a real-world function. For instance, the probability of correctness at an immediate or delayed test. And for example, if you define such a reward function, this would yield some kind of adaptive spacing algorithm. Or also you can define the reward function that you want to optimize, maximize or minimize, to be the minimum probability for of correctness on the contrary. And this would yield some kind of adaptive testing algorithm, and which will be the topic of our final talk from Fu Hualin, who will present us, as we said, an adaptive assessment algorithm based on Thomson sampling. And for example, a work that has been that has developed multi-arm bandits for improving student performance on several concepts is the work from Clément et al. In 2015 on multi-arm bandits for intelligent tutoring systems. And so I think I'm done here. So maybe we can go to our first talk. JJ, maybe you want to do a short break?
Yeah, we will start at 2:30. So if we don't have any questions so far. Yeah. So please move to the next slide.
Yes, maybe I can just give you the presenter.
Yeah. Okay. So okay, see you in 3 minutes for the next talk.
So JJ, should I get started?
Yes, you can start. Yes, we can hear you.
Great. Okay, so thanks so much to the workshop organizers for inviting me. So my name is Usha McKay from the University of Edinburgh. Okay, so I'm particularly interested in the question of how can we design teaching algorithms that enable human learners to become better at visual categorization tasks. Okay, so you might ask, why visual categorization? Why visual expertise? So one of the simple reasons is that many of the kind of tasks that we're faced with when we engage with the natural world can be framed in the context of categorization tasks. So, for example, you might be an ecologist or a naturalist, and you're interested in determining what species that you've seen. So again, from the image or from what you see, can you determine which of many different species it might be? Maybe you're a pathologist, and a large part of your job might involve looking at tissue samples and determining if that tissue sample is cancerous or not, or maybe contains the presence of other diseases. And so clearly these are kind of very fine-grained reasoning, visual reasoning that must be performed to be able to understand this. Similarly, you might be cooking your lunch and you really want to make sure that you don't eat something that's poisonous, and so being able to determine that is seriously important. Or you might be an art dealer, for example, and you want to make sure that you don't sell a forgery. So, I don't want to belabor the point, but there's clearly many problems in the real world that we face, that being able to understand what we see and being able to communicate that in some kind of semantic label is clearly very important. Okay, so one of the reasons, though, this is actually quite challenging is because in many of the domains I alluded to, there can be a lot of visual similarity between the categories of interest. And so, for example, we might have two species of birds here, and for a novice, it might be actually quite difficult to determine which characteristics or features or properties of those animals are actually important for determining which species it is. Another category of problems is that there's inherently can inherently be a large amount of within-class variation. So that variation might be due to simple things like the imaging properties, so how the photo was taken, the lighting, etc. But it could be due to inherent variation within the concept itself. So, for example, the appearance of the object might change due to its age or its location or its pose, for example. And all of these things make it quite difficult to be able to determine what something is. And finally, one of the main problems, I think, is this, maybe what I'll call an attribution problem, is that we have this really high dimensional object, which is an input image, and we have one semantic label that we want to produce, which might be the class label. But for a novice, it might not be clear which pixels are actually responsible for determining that. So we might be able to assume that it's probably not the background pixels, but which part of the actual animal itself is significant for determining the label. Okay, so I posit that machine teaching or computer-assisted teaching algorithms can have a huge role in actually enabling us as humans to be able to learn some of these domains much more efficiently and much more effectively. And I think it was set up really well in the last talk, but just to give a kind of a brief overview. So in some sense, we're going to have some student learner that's interacting with our system, and there's some target hypothesis that we want to teach them. So for example, that's the categorization task of interest. We'd love to be able to just directly implant those parameters into the brain of the learner, but unfortunately that's not possible. We don't know what model they're using. We have no mechanism to do that. And so instead, the communication channel we have with them is much more impoverished. So as this teaching algorithm that we have, what we can do is we can present information in the form of data, so images and associated labels. And we can get some feedback from that learner, maybe their estimates. And depending if we're teaching in some kind of interactive setting, we can also update our model of that learner online and determine what to show them next based on this interaction. Okay, and so just to make this more concrete in the context of teaching visual knowledge, we're going to assume we have access to a set of images with their associated class labels. And our teaching model is going to have a teaching algorithm, a model of the student learner. And what we're going to try and do is output a sequence of instructional examples, so images and their associated class label, to present to them. And the assumption here is that not all images are equally informative. So some images are going to be much more useful for the learner to be able to understand the concept of interest. And so that's where our big savings can be made by choosing intelligently which images might be useful. Okay, so I'm not doing justice to the huge amount of work that exists in computer-assisted tutoring, machine teaching, but there's broad different categories of work, from more theoretical work that maybe makes more simplifying assumptions about learners to be able to make some kind of theoretical contributions. There's obviously teaching beyond categorization in other tasks like decision making. There's a whole family of spaced repetition style models that we're going to hear more about later on today. And to some extent, there's been a bit less work in exploring this task of actual teaching visual knowledge and visual understanding to learners. And maybe how I characterize one of the limitations of some of the current work is that the information that's provided to the learner is quite impoverished compared to what they would actually receive from interacting with a human expert. So I'll expand on that a bit now. Okay, so a typical interaction with one of these computer-assisted teaching algorithms for learning visual knowledge or visual categories might look something like this. So you'd be presented with an image as the learner, then you're told to guess which of the species it contains. You'll make a guess, and then you'll get some feedback saying, okay, this is actually species A. And so, like I alluded earlier on, the problem here for the learner is you've got to now understand the mapping between the actual raw pixels in some sense and the class label to be able to learn something. And this is quite distinct from how you might actually learn or interact with the knowledgeable human learner. So for human teacher. So a human teacher, what they do is they'd likely actually highlight or inform you of which parts of the actual image or the object are informative for the category. So for example, in this case, the human teacher might say, you know what, for these two bird species, actually the Connecticut warbler has a complete ring around its eye, and the other bird, it actually breaks here. And once you know that thing, that's actually a real key to being able to do this, this particular task very effectively. Okay, so I'm going to spend a few minutes talking about some work that we've been doing to try and integrate this type of explanations into existing machine teaching algorithms. And so this is work with Usha McKay, Pietro, and Yisang. Okay, so the setup here is we're going to assume that we have access to a set of images. So I'll represent each image here as a dot in this low dimensional space. And so in this running example, I'm going to look at a binary classification problem. I'm not going to talk too much or at all really today about how we actually obtain this low dimensional embedding of the images, but you can assume that similarity or distance in this space encodes some kind of similarity in the input image space, or at least perceived so by the human learner. We're also going to assume that we have access to a per instance explanation, okay? And so there's many different ways that those explanations we could get access to them. So obviously we could get human experts to go in and manually annotate each individual image. That would be quite time consuming but possible. What we do instead in this work is we take advantage of recent advances in interpretable deep learning. So we can actually use deep networks that have been trained to do discriminative classification tasks and extract out explanations from those directly. And so in the very simplest way, these explanations basically encode which parts of the image are informative for the deep network, which clearly might not be aligned with what is informative for the human, but it's actually kind of like quite a simple proxy for that and something we can get for free. And so, for example, in this butterfly task, we see butterflies on top and these highlighted heat maps below. And so, for example, in the monarch and the viceroy, they're two very similar butterflies, but actually the deep network kind of correctly highlights this band across the image, which is something that's not observed, this kind of black band in the monarch, but it is in the viceroy. Okay. Right, so the other thing we're going to assume that we have access to is the discrete set of hypotheses, okay? So we've got our target hypothesis, which is the thing we ultimately want to teach the learner. So for example, here it separates the two different concepts, the two different classes. But there's also potentially a set of hypotheses that maybe the learners have a priori based on their own kind of inherent biases or knowledge. So for example, if you could say that the ground truth hypothesis somehow encodes something like the difference in the ring around the eye. It might be the case that me as a novice learner, before I know anything about the task itself, might group these birds based on their body color, for example, or their roundness, or the length of their bill. And so these are all kind of different schools of thoughts or biases that learners might have. And our goal really as a teacher is to kind of like invalidate those hypotheses and try and drive the learner towards adopting this ground truth hypothesis to be able to do this task effectively. Okay, so hypothesis H and teaching instances X and explanations E. Great. And so, yeah, the teacher's goal is to basically generate a teaching set of examples that's going to best elicit that target hypothesis of the learner. And so each entry in the sequence of teaching examples is, the image, the associated class label, and the explanation. And again, all of these things are available offline. We're not going to necessarily generate these things online. Okay, so like I said, we have very limited knowledge of what the learner actually knows. We're going to assume that this discrete set of hypotheses kind of reasonably well characterizes the space of possible knowledge that they may have. And so what we want to do is define a posterior over this hypothesis space, given the set of teaching examples that we've seen to date. Okay, so the teacher then can make use of this to be able to guide the selection of teaching examples to show. And so we're going to build on this model from Adish Singla from ICML in 2014. Okay, in the very simplest terms, we're going to have some prior over hypotheses. So there might be some prior preference towards particular types of hypotheses rather than others. And then we're going to model another term, which is basically saying how much does a given hypothesis H agree with the examples that have been seen to date. Okay. And so the simple intuition here is that if the prediction from the hypothesis agrees with the ground truth label, then the learner is not really going to change their mind. So there's no incentive to change your mind if what you believe is currently consistent with the information you're getting from the teacher. However, if there's a discrepancy, and so we can model this as the simple logistic function, you're going to downweight a hypothesis if it disagrees with the examples you've seen to date. Okay, so it's quite a simple kind of likelihood given the sequences of examples. Okay, so the other thing we're going to do is we're going to integrate the value of these explanations into the model. Okay, one of the kind of simple intuitions here is that, while we can generate explanations for all examples, not all explanations are necessarily going to be equally useful to the learner. And so what do I mean by that? So in this particular toy example, it might be the case that this I explanation is quite a good one. It might be that this other explanation, maybe it's valid, maybe there is something about the legs of the bird that are informative, but actually it's potentially not particularly useful or even understandable by the learner. And so what we'd like to do is be able to characterize how easily interpretable a given explanation is, so that the teacher then can ultimately bias its selection of teaching examples to the learner so that it selects ones that are easily interpretable, with the intuition being that things that are easy to interpret for the learner should allow them to more efficiently, or more effectively anyway, discount incorrect hypotheses. Okay, and so this is done just by simply introducing this another interpretability of explanation term. And so, for instance, examples that are more difficult to interpret will result in less discounting in some sense of incorrect hypotheses, whereas ones that are easy to interpret will have a bigger impact in downweighting the wrong ones. Okay, and so then the actual optimization itself that the teacher performs. So now we have this posterior with respect to each hypothesis, given the teaching set we've got so far. We've also can generate obviously an error associated with each hypothesis because we know the ground truth label, and so the hypothesis of interest, the target hypothesis that we want to teach, will have an error of 0. And so then the teacher's goal is basically to select items to add to this teaching set T that will result in the largest reduction in this expected error. Okay, so we want all the mass of this distribution biased towards the ground truth hypothesis. Okay, so I can give a very kind of quick toy example of how that might look in the context of this 2D example. And I'm not going to introduce the explanations at the risk of confusing things, but we have a set of hypotheses, okay? So each of these hypotheses, we've got our H star hypothesis that we want to teach that separates the red and the blues, and we'll start with the uniform distribution over these hypotheses. And so what's going to happen is the teacher is going to select items to show to the learner. And for hypotheses that disagree with that, they're going to be downweighted accordingly. And so, for instance, this hypothesis that was inconsistent with this prediction because it said that everything on this side of it should be red will get downweighted. And similarly, this will continue. So that at the end of this teaching, hope would be that the majority of the mass of the distribution is associated with hypotheses that are actually correct or consistent with the items that were shown so far. Okay, so I presented this all in the context of binary classification, but clearly multi-class is incredibly important, especially in these kinds of visual categorization tasks. And so in practice, we could represent a multi-class classifier for each of these individual discrete hypotheses. But in practice, what we do is we instead have an independent posterior for each class, and so that allows us to use this these same set of binary hypotheses, but instead share them in some sense across multiple classes. Okay, so let me very briefly talk about some of the experiments that we've actually done. So the setup is that we've got now our teaching algorithm, this model of the learner, and so we perform real experiments with learners on Mechanical Turk. And so they start with the tutorial phase where they familiarize themselves with our interface, this kind of web-based teaching interface. Then we teach them for 20 iterations on a task of interest, and then we test them at the end. And so this testing is just to measure their performance, but all the results I'll show later on will be results on this testing phase. Okay, so just to give an idea of what they see, so the learners will be presented with an image. They're asked to guess which species it is. They'll make a guess, and so for example, they say Viceroy. And if you remember from what I said earlier on, actually the Viceroy has this band across the back, so this is wrong. So then the teacher provides feedback and says the right answer is monarch, and here's this highlighted heat map of where to look for the informative features. Okay, so I'll present some results now. So we have experiments performed on several data sets. So one of them is this data set of images of a human retina. This is quite a nice data set because it's a kind of a domain where people won't necessarily have a lot of prior experience or knowledge of. And so there's 3 classes, and so these are representative examples from each of the classes, but in practice there's over 1,000 images. And we have about 40 participants per data set, per different teaching algorithm that we compare. And this, again, just to give you a rough idea of what these explanations will look like, we see these heat maps where they'll fixate on the actual, like usually on the thing that's quite discriminative for the class. So in this class, we have this kind of tearing under the retina, and you see that the teaching or the explanations have fixated on that. And similarly for the next concept. Okay, so as a baseline, it's always good to try and teach with random selections because actually it can be sometimes quite effective. So what I'm showing here is a histogram of the number of participants and their test accuracy. Okay, so what we'd like to have is like most of the mass of this distribution towards the right-hand side. That would mean that they're basically doing very well. But what we see here is we see this kind of big mode around maybe 30–40%, which in this 3-way classification task is effectively randomly guessing. So the summary here is that just randomly showing images to learners is not actually particularly effective in this setup that we have anyway. If we just show the explanations along with the images, again, no smart teaching, just selecting images at randomly but presenting explanations, there's a big increase in the performance. So these are distinct sets of learners, but still doing the same task. And finally, if we compare them to our teaching algorithm, we can see that there's, again, quite a big improvement overall. And so I'm only kind of giving a rough highlight of the experiments. There's further experiments in our paper with other teaching algorithms as well, and with and without our explanations. Okay, so here's another example teaching Chinese characters, again, just showing representative items from each class. And we have about 700 images in total that we want to use for teaching. And again, random doesn't do particularly well. With explanations, again, helps quite a lot. So it clearly enables the learners to kind of fixate on the informative parts. And actually with their teaching algorithm, again, we get a nice boost in performance. I won't go through this in the interest of time. Okay, and then finally the butterfly example we saw before. So 5-way classification. Here's some example heat maps. And again, we do pretty well and compared to other teaching algorithms that don't take into account these kinds of explanations. Okay, so I want to spend the last 2 or 3 minutes talking about what I see as kind of still big open challenges and questions that exist in this space of teaching visual knowledge. Okay, so the first one is teaching interactively. So I kind of glossed through things, but in practice, the algorithm that I presented is not interactively engaging with the learners. It's not taking into account their feedback. Instead, we're generating a sequence of examples offline. But it wouldn't be particularly challenging to add that in, but we need to then think about efficient teaching objectives. So this online optimization is not going to be prohibitively expensive, especially when we have a large number of learners simultaneously learning. Another thing that's particularly important, it was mentioned earlier on by Benoit, was this notion of space repetition style model. So again, teaching over long intervals is going to inherently induce some kind of memory decay on the behalf of the learner, and so we'd like to be able to take that into account when we're modeling. And so here, in contrast maybe to kind of like a flashcard type setting, where you're going to have to potentially take into account decay over instances of a class. So not just like the concept itself, but potentially even individual images. Yeah, kind of related to this question of like, how do we teach efficiently? If we really want to scale up to large numbers of learners and concepts. So for example, we're working with the Cornell Lab of Ornithology to try and develop teaching algorithms to be able to teach people to become good at identifying bird species. So here we might have on the order of like 10,000 potentially different bird species at the maximum that people could attempt to learn. And clearly like potentially thousands or tens of thousands of learners. So we need efficient tools to be able to do that well and be able to start robustly even with very limited knowledge of a learner, limited knowledge of the categories of interest. And so you can go to their website now and try out some of their simple quiz interfaces, but there's no teaching component in there at the moment. Okay, maybe the last one or two slides. Another big issue at the moment is these explanations I presented, while they're effective, they're clearly very simple and not actually particularly grounded in real world semantics. And so, you know, here's an example of, again, an image of a human's retina. And it's clear that there's a kind of there's a language that's used to describe the various different properties and features and attributes of these images that when combined together will enable a learner to be able to talk about a particular disease, for example. And so it might be suboptimal if we were able to teach people by bypassing this shared vocabulary, because they're going to lose out on this ability to communicate with others. So we need efficient and effective ways for getting more human interpretable explanations out of these data sets. And one more example, I think that kind of is a future challenge, but also kind of a cool future direction, is it's kind of closing this loop between the deep networks we have now for doing discriminative learning. For example, here's a paper from 2 years back where they showed that they were able to classify properties of images of retina that weren't thought to be possible to determine visually before. So for example, they could determine the age of someone quite accurately, or the gender or their smoking status. And so here's a scenario where now we can train models with large amounts of data to be able to perform these tasks. And this gives us the potential to close this loop where we could actually go back and teach humans to be able to do these types of tasks that maybe weren't previously thought achievable. Okay, so thanks very much for your attention. So if you're interested in that particular paper, there is a GitHub page here that has access, or that has code for the model and some baseline teaching algorithms. We've also got some data that we've generated from it, but also there's access to teaching GUIs and interfaces. So, you know, you can kind of plug your own teaching algorithms into those and very easily run those kind of experiments on Mechanical Turk. So take a look at that GitHub page if you're interested. And that's all for me. Thanks very much.
Thank you very much. So Usha McKay is a professor at the University of Cambridge, and I was too much in a hurry, so I didn't present him. So feel free to ask questions. Thank you very much. And I may even try to open the mics for everyone to try. But for this first part, before the 15 minutes break, the University of Edinburgh, sorry.
Edinburgh, yeah, I was going to
yeah, sorry. So I wanted to know, like, what in this technique, so that seems to be really easy to generalize to different ways to have visual explanations.
Mm-hmm.
So what, for example, like in your algorithm is so specific to the fact of selecting, like, let's say, linear hyperplanes, I mean discriminative features, and what can be generalized to more ways to have visual features such as attention models and so on.
Maybe, okay, I'm not sure if I get your question. Let me say something and then you can come back to me and say if I'm if I'm answering your question, if I'm going off on a tangent. So you know, in some sense what I presented is actually quite straightforward. So, you know, we've an automatic method for generating explanations, then we have a mechanism to kind of to take into account the utility of those explanations. And in some sense, that's a kind of a very practical reason, because sometimes these automatically generated explanations are going to be terrible. And so if we have a method to make sure that we can kind of get rid of useless ones, it means that we're not actually, the worst case scenario is we would show a learner potentially a useful image, but give them such a bad explanation, it could actually make them learn much worse. And so I think that there's a lot of scope for basically changing up many components of that kind of system, in the sense that you could have a much more sophisticated model, learner model that incorporates some notion of like visual attention, for example. But if you can have a way to integrate some notion of like a mapping from those like features they're attending to and the actual like label itself, or a way to guide their attention, that in some sense I think kind of fits into that framework quite well.
Okay, thank you. And you do have a questions I didn't see at the right place. So how do you deal when having plenty of images? So if you use the same bird picture, each time you want the user to learn to recognize the species, the user will learn the particular picture. Otherwise, you would have at least as many pictures as reviews. If you expect that a user may need to have 20 questions to learn a species, you would need 20 distinct pictures. So maybe making the set of questions is going to be complex, especially since you need to ensure there is not a single mistake in the sets.
Yeah, okay. Oh, go ahead, Tony.
Yeah, so I think it has something to, like, how do you, what is a question, what is a visual explanation in what you showed? Yes.
Yeah, again, so again, I'm not sure if I'm getting to the heart of the question, but so, one thing in this particular domain, the birding domain, we actually have a crazy amount of data, more data than we could ever actually sit down and teach someone with, because there's constantly people uploading these types of photos online. So that's where the teacher can really provide value, because they can select examples that are useful. And the challenge in some of these instances is that there inherently is a large amount of variation within the class. So if you had tried to teach some of these species and only used a kind of a flashcard style approach where you had one iconic image for each class, it isn't going to be enough to capture the variation that might exist in there. So the goal really then for the teacher is to make sure that they choose examples that are kind of representative of the main modes of variation within the actual concept, and not actually to select, outliers that might be quite high value in terms of like their distance from hyperplanes, but actually not particularly informative. And feel free to come back to me if that didn't address the kind of root of your question.
Yes, I also want to. So what I feel quite amazing in this talk is the fact that all the explanations are automatically generated, and then you have your teaching algorithm in order to find which ones are the best, makes the most sense in order to identify the correct class. So what I would like to know is how you can extend it to other types of features. So for example, what I mean is the fact that usually in this kind of, let's say in this kind of community, it's hard to get some experts telling like this is the right feature, but here in your case, you can automatically generate it. So do you think it could be also applied to even like other kinds of data? So not necessarily images, but like let's say a text in which you could find where is the solution in order to answer the question. Yes.
Yeah, no, definitely. I mean, so, the reality is that even if you have access to an expert, they might not have the patience to go through and give you all the explanations. To be honest, they might not even have the knowledge themselves to be able to verbalize those things. They've kind of embodied the task so well that they've internalized it so well that they're not capable of actually describing well. So just because you're an expert doesn't make you a good teacher. So having an automatic method is very attractive. And so yeah, extending to different domains. So you can imagine, in text, what would that mean? Maybe it means highlighting, like if it's a passage of text, it might involve highlighting some informative subset of words or whatever. But the other big question would be much more sophisticated, higher level explanations, like in a mathematical setting. Like those are the kinds of things that we love to be able to provide that might give true insight, but might right now be outside of the reach of kind of automatic methods for generating explanations. But I think hopefully what we showed is and it's kind of obvious, the value of these explanations can be huge even when they're quite simple.
Okay, so I opened the mics, so please feel free to. So you do have a comment about the fact that you said indeed some people understand things in a personal manner, so some more towards iconic or mental mapping techniques, while others would have other ways to learn something. So yes, I didn't open the chat, but I did open the the mics. So if someone wants to just connect their mic, and if you can't, it's because maybe you might be in the. So like we will still have a discussion during the open discussion.
Yeah, I'll definitely be around for the discussion, and I'm also super happy to take questions offline if some people want to email me or send me messages on the private chat, because I don't want to take away time from the next speaker. But definitely feel free to contact me if there's any questions, anything that wasn't clear, or any kind of ideas.
Thank you very much. So we will now move to the next speaker. I will change the slide.
And you'll have to disable my camera, JJ.
Yes, I will do. Sorry. Yes. So, okay, up. So, Hiroshi, can you turn on your mic? I feel you do. So your mic is open, but we don't hear you yet. Yes, okay. Okay. So we see you, but we don't hear you right now. So you might try to reconnect and or just cut and come back. Yes. No, we don't hear you. Okay. So I really suggest that you just refresh the page and come back and turn on to put back your mic, and I'm pretty sure it will work.
So maybe if it's a connection issue, maybe you should just don't put your video and just your audio. Yes. Maybe try that.
Hello?
Yes, it does work now. Yes.
Okay, I refresh my page.
So I will present you. So now we welcome Hiroshi Tamano from NEC, who will talk about non-compensatory knowledge tracing. You can start.
Yes. Okay. Thank you for introducing. My name is Hiroshi Tamano, and I'm working for NEC and studying at Graduate University for Advanced Study. So Daichi Mochihashi is my supervisor. So in this presentation, I'm going to talk about non-compensatory knowledge tracing with local variation approximation. So here is the outline of my talk. So first, I explain the background and the purpose of this study, and then I describe the proposed method, generative model, and posterior and parameter inference. And then I show you some experimental result and make conclusion. So the first part is background and purpose. The beginning of our background is knowledge tracing. And knowledge tracing is a machine learning task to trace learner's latent skill and predict whether he can solve a next problem or not. So here you can see the system, learning system, and users. The user interact with a learning system. Learning system gives you problems, and user solves problems. And the learning log here is stored in the learning system. The learning log is a sequence of answers to questions, to problems. So when you look at here, the user 1, he tried problem number 2, it was correct, and then he tried problem number 4, it was incorrect, blah, blah, blah. So we have this kind of data set. So knowledge tracing trained the model, predictive model, and then once we have new user, the knowledge tracing predict the future response. So for this user tried problem number 5 and 9. So what the future response will be? So the ray tracing predict whether he can solve this question or not. So the ray tracing can be used in a personalized education, such as recommending the next question you should solve. And ray tracing has been studied in the state space model, recurrent neural network, factorization. So when we look at the state space model, there are 4 categories regarding model which handles problem requiring multiple skills. So one aspect is a latent space. It is binary or continuous vector. And second aspect is the emission probability. It is compensatory or non-compensatory. So when we assume the compensatory as assumption, it means that each skill can complement other skill. If you assume non-compensatory model, each skill cannot complement other skill. For example, when we consider the problem 1/5x plus 3/10 equals 2x. So when you solve this problem, of course, you need fraction and equation skill. And the fraction skill cannot complement equation skill. So in this case, the non-compensatory assumption is very natural. So we organize these 4 categories in this figure. So the latent skill is binary or continuous. The emission probability is compensatory or non-compensatory. So these 3 place, there is existing work, but the place here, non-compensatory and continuous model, is unexplored. So the purpose of this study is to explore the potential of state space model, which has continuous skill state and non-compensatory emission. So this model is expected to give accurate prediction and natural explanation. So compared to the binary scale state, continuous scale state is expected to give accurate prediction. And compared to compensatory model, non-compensatory model is expected to give natural explanation, as you see in the example of fraction and equation problem. So here's the that's the purpose of our study. So next, I'm going to describe the proposed method. So first is a generative model. Our generative model is, roughly speaking, the linear dynamical system, except that the emission model is non-compensatory multidimensional IRT. So here the graphical model of our generative model, which is a typical state space model. So here you can see the latent states, sequence of latent states. So Z, J, T represent Lerner J's latent scale at time step T, which is a k-dimensional continuous vector. The k is a number of scale. And Y, JT represent the student response, Lerner's response. So Lerner J's time step T's response, which is 0 or 1, representing incorrect or correct. And X is a covariate. And so the covariate is the scale transition happened related to the previous state and also the covariate. So we can design any covariate in this variable. So like we introducing some getting curve in this covariate. So in the next 3 slides, I will define the initial state probability and state transition probability and emission probability. The first is the initial state probability. The initial state is drawn from Gaussian, which is same as a linear dynamical system. So I skip this slide. And next is the state transition probability, which is also drawn from the Gaussian distribution. So the previous state is linear transform, and also the covariate is linear transformed. So we can the next state is drawn from this Gaussian distribution. This is also same as a linear dynamical system. And the last part is the emission probability, which is the different part from the linear dynamical system. We use a non-compensatory model in multidimensional IRT, which is represented as a product of sigmoid function. Here, the K is the index of scale. So G, J, K, T is a latent scale state of lambda J and scale T, scale K and time step T, and BIK is a difficulty parameter for question I and scale K, and AIK is a slope parameter of sigmoid function for problem I and scale K, and QIK is a question scale map, which is 0 or 1 if problem I required scale K, QIK is 1, and if the problem I doesn't require scale K, it is 0. So we can visualize this probability function like this. So as you can see, if you have both scale, here is a 2 scale. So if you have both scale, you have a high probability to solve this question. Otherwise, you have low probability of solving this question. So that's a non-compensatory model. So far, I explained the generative model. So next step is the posterior and parameter inference of this model. So in linear dynamical system, posterior inference and parameter inference can be executed through forward-backward algorithm and EM algorithm. So we want to fully utilize this framework. So to applying this framework, the obstacle we have is the forward alpha message. The alpha message is written as a simple Bayesian update loop. The posterior here is proportional to the likelihood and prior. In linear dynamical system case, the emission probability here is Gaussian. And also the prior is also Gaussian. So the posterior is Gaussian. We can obtain the exact inference, exact posterior by we can obtain analytical solution. But in our case, the likelihood function is multidimensional IRT. So it's very hard to obtain the exact posterior in an analytical form. So we are going to approximate this likelihood function as Gaussian. So once we approximate the likelihood as Gaussian, we can treat our non-compensatory KT, just like linear dynamical system. We can use the posterior inference of the method proposed in linear dynamical system, and parameter estimation can be also done with the typical linear dynamical systems algorithm. So now we are going to approximate this likelihood function as Gaussian. And we use the local variational method. So what is a local variational method? The local variational method is proposed from Jacra and Jordan 2000. In their case, their likelihood is sigmoid function and Spreyer is Gaussian. It's very similar case to our case. So roughly speaking, their method approximate a likelihood around the prior, and it gives accurate posterior approximation. I'll give you intuition from by using these figures. So the prior is here is Gaussian, the green Gaussian, and the likelihood is blue. So their method find variational lower bound in an exponential quadratic form. This is Gaussian. So in the place where the prior exists, so their method locally approximate the likelihood. They don't care about the place where the prior doesn't exist, like here. So using this Gaussian approximation, their approximated posterior very precisely approximate the true posterior. So we're going to use this local variational method to our case. So what was the target likelihood function to be approximated? So we have the likelihood function for correct answers and incorrect answers. In the correct answer case, the likelihood can be written as just a product of sigmoid function here. So just applying the Jacra's method for its sigmoid function gives us a local variational, local Gaussian approximation. So the correct answer case is very easy. And in correct answer case, we need more steps. So this slide shows just a rough image to approximate likelihood for incorrect answers. So there are two steps. In the first step, we make the likelihood function one-dimensional likelihood function through this gradient direction. So now our likelihood is a 1D likelihood like this. We apply the Jacra's method to obtain the one-dimensional lower bound here. And in the second step, we extend this 1D lower bound to the multidimensional case. So we have to fix the variance in the direction of S1, this direction. So even if we set any of the variance, the lower bound is lower bound. So there is no information to decide. So we just copy the variance of prior to this lower bound. So we get the final multidimensional lower bound like this. So far, I explained the generative model, and the only difference from the LDS is the emission probability. And emission probability, I explained the approximation method, approximation as Gaussian, so that we treat our model just like LDS. So we can proceed the posterior inference and parameter estimation proposed in the LDS. So I'm gonna show some experimental results. I did 3 experiments. First experiment, approximation of alpha message and prediction performance and visualization of explanation. The first is approximation of alpha message. There are 2 cases, correct answer and incorrect answer. I just showed 2 cases for each. So when you look at the case A, so the red counter is likelihood here, and green is posterior, prior. So given the prior and likelihood, our approximation gives the approximation of likelihood here, the blue counter, and then the lower panel shows the true posterior and approximated posterior. So you can see our approximated posterior is very accurate in the correct answer case, and compared to the correct answer case, the incorrect answer case have slightly different from the true posterior. So in incorrect answer case, the variance is underestimated, but the mode of the distribution is very correct, I think. In this slide, I show you the result of prediction performance. I used assessment dataset, and I just used main questions, which is answered by more than 10 learners. And we compared our model with DKT and DKVMM, which is a deep learning-based method. So you see our model shows slightly better results compared to the deep learning method like this. So in this slide, I show you the visualization explaining why a learner cannot solve a problem. So one big advantage of non-compensatory model is to be able to explain which skills and how much skill are missing when he cannot solve a problem. So here's a visualization. So in this example, in this case, the problem is require 2 skills. One is subtraction whole number, and second is absolute value. So this dotted line is a threshold, and this guy is predicted that he cannot solve this problem. So he need to improve. He need to train skill number 1. So to answer this question correctly. So how I can get this visualization is by using the inferred learner state and item response function. So this blue Gaussian represent the inferred learner state, and the red lines represent item response function as a counter of item response function whose probability is 0.8. And the red area is an area whose probability is more than 0.8. So I approximate this red area using 2 dashed line. One is vertical and the other is horizontal. The threshold 1 is regarding the skill 1, and threshold 2 regarding skill number 2. So if you have skill number 1 more than threshold 1, you have more than 0.8 chance to solve this problem regarding skill 1. And if you have a skill number 2 more than threshold 2, you have more than 0.8 chance to solve this problem with respect to skill number 2. So using this threshold value, we can draw this kind of bar chart. Okay. So I'm going to make a conclusion. So our purpose of this study is to explore the potential of state space model, which has continuous skill state and non-compensatory emission. And our model is combination of linear dynamical system and non-compensatory multidimensional IRT. And we propose a local approximation to the likelihood function so that we treat our model just like LDS. In our experiment, we show our variational posterior adequately approximate the true posterior, and our model achieve better prediction accuracy compared to the 2 popular deep learning-based method. And lastly, I showed you visualization explaining why a learner cannot solve a problem. I think which is informative for the users. Okay, thanks for hearing my presentation.
Thank you, Hiroshi. So do we have questions from the audience? So you can ask questions in both shared notes or on the chat.
Mm-hmm.
I do have a question, which is, could you please go back to your not emission probability, the one before, the transition probability?
Transition probability, okay.
Yeah, thank you for the visualization, which is interesting. Yes. So
yes.
Here I understood that you have this linear dynamical system, but do you think it could take into account the time lag between 2 observations? So for example, does it treat similarly like 2 steps which were like 1 day in time than 2 steps that were 1 year in difference in time?
Yeah, I'm thinking we can treat that difference using this covariate. So we, if we design this covariate to include the time which taken from the last training time, I think we can treat such kind of difference. Okay.
Do you think it would it's better not to assume it, or it would make the model better, or this kind of regularization? Do we have other questions? So I also wanted to ask, you showed that you had superior performance to methods like deep learning, deep noise tracing. So it could be surprising because, for example, like you're having an approximate posterior, and you're kind of fixing the dynamical system. So could you elaborate more about why you get better results while having an approximation? Do you think it's related to the fact that it's a non-compensatory model, or for other reasons?
I think when I read some paper of night tracing, some very simple model even outperformed the DKT and DKVMM. So such as the researcher from Newton, which is the adaptive learning company in the United States, proposed hierarchical IRT. So their method is very simple, even though they outperform the DKT. So I'm not sure why their model outperformed the DKT, but I think that even a simple model, there is a chance to outperform the DKT. So I think the DKT and DKVMM, how can I say, it's a very flexible model, so they need more regularizer, I think. So the simple model just outperform because of the model complexity.
Okay. Thank you. And so also yeah, Benoit added a reference to the paper you were mentioning from Kevin Wilson from Newton in the chat, so everyone can read it. Yeah, and maybe a final question before we move to the break is the fact that so you showed that the fact that it's interpretable. So my question is, do you need to know the Q matrix to know which skills are required for an item, or do you think you could learn it directly?
In my current opinion, I think we need the Q matrix, since for user, people want to understand by the name of the skill. So in that sense, the Q matrix is needed. So that's why I model the KT using the K matrix.
Okay, thank you very much. So
thank you very much.
And yes, please, Hiroshi will stay here, even if it's late in Japan, for discussion, so feel free to ask questions.
Thank you so much.
So now we will move, we'll have a 15-minute break, and we will then move on with our next talk. So I will prepare the slide.
Jill-Jênn from the University of Chicago. And Jill will be presenting a work that has been previously accepted at and presented at Europe's 2019. And it's a work on adaptive spacing algorithm, and especially it's called Teaching Multiple Concepts to Forgetful Learners. So now, Jill-Jênn, if you want, you can start your presentation. Thanks.
Excellent. Thanks a lot. Thanks, Benoit, for the introduction. All right. So hi, everyone. Thanks for attending the talk, and thanks to the organizers for inviting me. I will mainly discuss like one of our recent work on teaching forgetful learners in the next like 25 to 30 minutes. And as like some of the previous talks already covered, like there are a lot of aspects for human learning when we in practice. If we think about designing algorithmic tools or automated algorithms for interacting with the learner. So this particular talk is relevant to modeling the kind of psychological effect of learners' behavior. We're trying to take into account of the forgetful phenomenon for human learner such that we can design the optimal tools for interacting with them. So the work is joined with quite a few amazing colleagues. So Anit and Manu and Adish was from the Max Planck Institute, and we have Ocean who is still in the audience here when we collaborate at Caltech. So Pietro and Ison is from Caltech, and Andreas is from ETH Zurich. All right, so let's start with the motivating application. So we know in like nowadays modern teaching apps such as Duolingo or Memrise, it has a like tremendously large user base. There's like approximately over 300 million students by the year 2015. And the app basically works based on this spaced repetition practice. Okay, so we know that in practice, the human learning and machine teaching requires repetition. So because human has an intrinsic forgetful phenomenon, we need to take into account of like what is the how can we properly model the human's learning rate and the forgetful curve in order to better design a good sequence of teaching instructions so that we can optimally interact with the user. And the goal for this project and for this language learning automation in general is to find an optimal personalized scheme for repetition so that we can design the best teaching policy to make it the teaching work practical. So here's like a sneak peek of the system that we are deriving. Okay, so there's a small lab in this project. So we basically want to have an online teaching system personalized to human learning, and it actually adaptively interact with the human user in the following protocol. Imagine that we're trying to learn a foreign language by flashcards. In this case, we want to learn German by like looking into a sequence of pictures of words, and we show kind of the English translation of the word, and then the user get a chance to perceive what this word means and how we relate that to a practical object. And then so if the user doesn't know the word, we expect nothing from the user, maybe a guess, so that we get some prior knowledge on the user's current knowledge state. And if the learner, for example, answered the translation wrong, right, the teacher will provide some kind of feedback mechanism. In this case, we want to show that there's a toy, and if the learner enters some answer which is not exactly a toy, the teacher provide the correct German words, and hopefully the learner can perceive it, remember it, and make fewer mistakes in the future rounds. So the algorithm iterate in rounds. At the first iteration, the teacher displays a flashcard. And for say we have a total number of n objects to teach, or n concepts. And the learner is going to make a tap to guess the answer for the flashcard based on the current knowledge it has. Let's denote that by a binary random variable y as the recall rate, like whether the learner gets the answer correct or not. And depending on the feedback, the teacher provides the correct answer and proceed to the next round. Right. So as you can see, the goal for teaching here is basically come up with optimal teaching sequence such that you can minimize the recall rate. minimize the false prediction rate. So in the figure down below, we're showing basically one illustration of the system we use in our user study. So the algorithm proceeds in rounds. At every round, we have these 3 atomic interactions between the teacher and the learner. Okay, so I'll come back to the teaching application later towards the end of the talk. But let's first get a bit deeper look into the existing work and the background for this field overall. So I'm still seeing a black screen. Oh, sorry, a white screen in front of me. Just wait for maybe 2 seconds for the slide to show up. Oh, okay. So strange, I couldn't see the slide.
Okay,
let me just,
we do see the slide, but yeah, if you cannot see the slide.
If I just advance 1 step, do you see the slide 5 or slide 4 now?
Yes,
Yeah.
it's Pimsleur method.
Okay, sounds slide 4 is empty. Okay, good. I think that's the animation. Okay, thanks for letting me know. All right, so I'll just back up 1 slide. All right, so let's consider one example teaching scenario. Like we have a total number of 5 concepts, and we want to teach the 5 words in 28 different rounds, right? So within a 28 times the budget, we can allocate how frequently show a word sequentially. And our goal is to maximize the rotation rate. So existing approach, as we can imagine, like there's one very basic approach, basically just show items at random, right? So we have A, B, C, D, E. And at every iteration, we show one random item, hoping the learner can pick it up and disregard the learner's customization, like the feedback mechanism, same as round robin, right? In the round robin policy, we're basically showing the words in turn. Even though the learner make perfect guess over all the words, we still repeat that for like 4 times. And one obvious drawback for this kind of non-adaptive algorithm is that they disregard the learner's feedback mechanism. So we potentially have a huge room for improvement if we want to maximize the utilization of the limited budget, which is the time in this case. So that basically leads to a like slightly more intelligent algorithm, which is actually very popular in the mainstream teaching practice, introduced by Pimsleur in 1967. So the idea is kind of it's simple, but it kind of uses the space repetition for the first time, like in a popular way in the literature. Right. So the system works as follows. We have consider the user's spacing and lag effects, right? So Pimsleur used audio-based language learning program, which is now franchised by Simon and Schuster. So refer to this method as a graduated interval recall, where he wants to teach a vocabulary, and vocabulary is introduced and then tested at an exponential scale. So we test the user at, say, day 2, and then day 4, and day 8, and so on. We just like repetitively show the same item, but still there's a common drawback as the round robin and random algorithm. It doesn't take into account the user's feedback, right? And then as time moves on, 5 years later, so Lightener actually introduced an adaptive teaching system, which truly takes into account of learners' feedback. And there is so-called adaptive spacing intervals, which he kind of designed experiment also for language learning, where he put like into the vocabulary of words into multiple time beats. In this illustration, for example, we can see like items that place in a 1-day interval B and 2-day, 4-day, 8 days. And we show the words according to how fast that how frequent we should show each word. And if the user say answer the recall query correctly, then that vocabulary word get advanced into the next time beat, So we show the item less frequent. But if vocabulary word happen to be answered falsely, then you get demoted into the previous bin. So in this case, we have kind of a systematic way to change the frequency of the words based on the user's feedback. So this is actually very effective in practice, but we do have one concern about this algorithm, mainly because there's no guarantee in optimality of the algorithm. By optimality, I mean, we want to find, say, an algorithm that, if we compare the retention rate for a fixed time interval performance, then want to say we can guarantee that this algorithm we're running is not too much different from the best ever algorithm that could be developed under the same condition. So we want to kind of have some rigorous theoretic guarantee to make sure that the algorithm will work well, in particular, will work near optimally. So basically, across this talk, we're going to make an effort and try to make a rigorous argument saying that there are conditions that exist such that we can claim under this condition algorithm actually behaving near optimally. Great. So that's basically it for the background part. And I would basically proceed to talk about a particular model of humans' forgetfulness or humans' memory for learning, in particular for the perhaps simplistic setting of learning concepts. So we're just trying to teach students or learn to memorize rather than teach people to generalize. So that's another topic I'll probably briefly mention towards the end of the talk, like how to teach people to learn a concept by showing them training examples. In this case, we're just showing them exact concept and hope them to memorize. So back to the story. So Settles and Meter basically introduce a learnable model for humans forgetful curve in ACL 2016. So the half-life regression model actually exists long in the literature, but this work is basically the first one trying to come up with a machine learning based approach that tries to learn for a particular group of human learners what is the model parameters that we should fit. Okay, so the half-life regression model is basically modeling the forgetful curve in an exponential trend. Okay, suppose this pi, the small pi, represent the learner's recall probability. Like given the history of like words that we have already shown to the learner, and which we can model the probability of recall at a future timestamp by the end of history, t, as exponential decay curve. And so this curve get half at every delta ti over hi iterations. Hi is a hyperparameter we can control. We can fit for a particular group. Every different group for different i has a different hi. And this ti is basically showing what is the time difference since the last time we show the same word again. In this simple illustration, so we see like for one concept, if we show that at timestamp 0, then the probability of being correctly recalled decay by half at timestamp 1, and then further decays next time we show it. If the learner answered correctly or incorrectly, depending on feedback, we adjust the half-life regression curve. So the half-life actually, I think I lost control of my slide.
Oh yeah, I think there has been a problem. So I'll give you the control back. Sorry about that.
Okay, no problem.
Okay. You should be good now.
Yes, got it back. Thank you.
Sorry.
No problem. All right, so I was basically here saying the parameter hyperparameter hi for every concept for a user group is parameterized by like ai and bi, where ai and bi is the number of times that the user answered the query correctly, and bi is the number of times the user answered the query falsely. Right? If we observe a sequence of feedback, then we can adjust the learner's forgetful curve accordingly, and we can design a teaching policy accordingly. Good. So now we have a basic learner's memory model. Let's see how we can deal with, how we can manipulate that such that we can design a policy that exhibits some kind of guarantee. So recall that we have this interactive teaching protocol where we have capital T rounds. At every round, the teacher chooses a concept among one of the small m concepts. And learner tries to recall the concept. And depending on the feedback, the result of learner's recall, the teacher updates learner's memory model accordingly and review the answers so that the learner have a better chance of remembering the concept. And we first propose a surrogate objective function by basically imagining what is a good, like a rigorous quantitative measure to model the learner's performance. It could be exactly the recall probability for every word at the final stamp, but it could be something that maybe like behave in a monotonic way, but is easier to analyze if we think about from a mathematical sense. So our particular choice of the surrogate function is this following area under the curve expression. I'll just explain this briefly without going too much into the details, just from a motivational level. So we see that for a fixed concept, let's like fix the concept to be I among m possible concepts. We're just going to look at the overall forgetful curve from timestamp 0 to timestamp capital T. So this is the end of our budget. And we draw the learner's forgetful curve. The learner's memory got decayed by, according to this half-life regression model, based on the learner's recall. So at every delta function here, we're basically showing the item again. And depending on learner's feedback, we update the curve accordingly. So now we show the item 3 times. The learner has a forgetful curve like this. And just compute the area under the curve across the entire teaching horizon. Okay, so in this case, for item I, the utility that the teacher gets or the learner gets towards the end is just modeled by the area under the curve. And then we sum over all the objects. That is basically our surrogate function we want to optimize. In the extreme case, the learner performs extremely well. Every time it just remember it perfectly, and we get absolute maximum for the area under the curve for that particular concept. So that kind of indicates the objective function is monotone with respect to learner's performance, which kind of hints it to be a good measurement of performance. So our goal here is to maximize the surrogate function, and our guarantee is going to be made with respect to that objective. If we consider the baseline approaches we have talked about before, let's think about the drawbacks now more rigorously. So we talk about round robin, where at every iteration we just show item in a sequential way in a fixed order, and doesn't adapt to the new estimates of learner's recall, and it could overly repeat the easy concept, and intuitively we can't get any guarantee for that. At least we didn't in practice. And there's another like kind of intuitive approach which we can consider. Actually, it could be viewed as generalization of the popular Pimsleur and Lightener system. So that corresponds to the lowest recall probability heuristic, where if you look into the forgetful curve, every iteration, we just look into all the m items, and we find the item that has the lowest current recall probability. So that one seems to be pretty heuristic. Well, it is adaptive based on the learner's feedback. We can update a different forgetful curve. But unfortunately, we don't have, we didn't derive any guarantee for this particular algorithm, so that I would just focus more on this greedy algorithm based on the surrogate function, which I just introduced one slide ago. And one potential drawback for this lowest recall probability is that it doesn't consider the change to the recall probability. It's just looking into the current recall rate. It doesn't change how much worse it is before and how much better it is in the future. So that is one possible conjecture that we've made, that we can't derive a rigorous guarantee for that. Okay, so the algorithm which we're going to analyze is going to be greedy algorithm, adaptive greedy algorithm, based on the surrogate function we just introduced. Right, so at every iteration, we have a history. and we just check for every new item, and with respect to the current posterior of learner's answer, we add the hallucinated answer of the learner of that item, like whether the learner recalled the concept at timestamp t correctly, and we compute the expected benefit based on the surrogate function. And so this F function is calculated based on our half-life regression model, which could be learned from the group of learners before they come into our system. And the greedy algorithm just pick the concept that maximize the expected gain of the item. Okay. The algorithm is very intuitive. It's probably not much to explain in terms of the basic mechanics. And then what we care about is how this algorithm performs, why it is a better algorithm to study, given that we don't have much chance in analyzing the baselines we have so far. So I want to characterize the behavior of the objective function based on the following two criteria, which also kind of exhibits the challenge of this problem. First, we know that this objective function is not sum-modular. What it means is that the gain of adding a concept, it can actually increase if we have a longer history. There's no diminishing return which kind of demotivate the usage of the greedy policy. Because if we pick an item, the item could have a future higher gain. And we don't have much confidence in whether we're making a good choice of this particular item or not at this current timestamp. But we can kind of quantify the degree of violation of this diminishing return by looking into this notion of sum-modularity ratio. So not going into details of the exact definition of this gamma parameter, but this basically says if we have a big gamma, it is like the performance of the system might be bad because potentially we could expect it a much higher surprise in the future. So and that also motivates our next quantifier of the behavior of the function, which is we refer to as the curvature of the sequence sum-modular function. We see that the function, the objective function f here we use, is not even monotone. By that I mean if we like look into two sequences, one longer, like it's the orange and the blue, like we show the item 4 times, and the blue is just showing the item 3 times. Looking into the area and the curve, actually we can see the blue curve has a higher utility if you look into the area and the curve. But again, we can use another parameter to capture how much violation the objective function has with respect to this property for monotonicity. And we know that greedy works well for monotone function. And hopefully if we capture how much violation the system has with respect to this monotonic characteristic, we can regulate the behavior of the greedy algorithm theoretically. Good. So equipped with these two parameters, what we basically show in the paper, a detailed analysis in the actual paper itself, that the performance of the greedy algorithm is actually bounded by like a fraction away from the optimal. So if you see like this is the best algorithm that one can ever develop, and this is the algorithm we're running, the utility is not too much different, where the difference is bounded by this factor. And we know if it is close to a constant or some fractional value, then we could be confident that the algorithm is performing well. So in this case, we just concretize the bound as a function of the curvature and sum-modularity ratio. So that's one result for basically general memory model. It is not restricted to half-life regression. And we also have a more absolute performance bound for the half-life regression model, which kind of reason about how much give a sufficient condition for the algorithm to be performing well for like particular choice of the parameters of half-linear regression. We say for basically a particular type of learners, we can say running the greedy algorithm is always going to give you a 1 minus epsilon high utility. So that's kind of some different flavor, but for the interested readers, I refer you to the papers for the detailed analysis. Good. Hopefully that gives you a flavor of what kind of tools we're using to analyze the performance of the sequential teaching algorithm in an adaptive way. What I'm going to show you, I think I'm probably a bit short in time, but I'll just show you what we did in terms of the empirical user study to validate the performance of the algorithm. So this slide you see is just one illustration of the theoretical behavior. We're testing out different algorithms using different teaching policies. And we actually show that with respect to objective function, the greedy algorithm is performing at pretty close to the optimal algorithm, which we run by exhaustive search. And round robin, which doesn't take into account of adaptivity, is performing not as good, evaluated by the objective function, which is the area under the curve. Okay, so we did a real-world user study by designing a teaching interface that kind of interleaves between these teacher and user interactions. So we recruit 150 participants from Mechanical Turk, Amazon Mechanical Turk, and we're trying to teach 15 concepts over a total number of 40 iterations. So there is a proper spacing between the occurrence of every vocabulary word, and based on the feedback, we basically adjust the system's recommendations. And the total study times last over like roughly about 30 minutes, less. There's a 5 minutes slack, 25 minutes in total for the user study for each user. So we compared the performances of different baseline algorithms, which we refer to as the lowest recall. This is kind of a generalization of the Pimsleur and Lightener system. Random, which does not take into account of the adaptivity, and round robin, which is a fixed order, also doesn't take into account of the learner's feedback. So the greedy, this is basically the final score of the learner, like 65 on average score for average learner over the user study for greedy, which is like marginally higher than all the other baselines. And concretely, we basically run the experiments for several different types of tasks. For example, we try to teach.
Sorry, I think your slides are all white now, all blank.
Huh.
Yeah.
So
and maybe can you conclude in maybe 5 minutes, Ushin, please?
Of course, yeah. Yes. So I have I have 3 more slides basically. The 2 slides which is right now blank. Hopefully you can see the link later. Those are the showcase of the data sets that we use, like what kind of words we're teaching. So we're teaching German. We're teaching about diversity, which covers some species and has hard names. Some of them easy names, so we can showcase there are concepts that the user can recall easily, and there are concepts that takes basically many more iterations for the human learner to master. And the performance is basically highlighted in the slide you just saw. Okay, so I'm jumping to the last slide. Hopefully that shows. Great. Okay, so that's a summary slide I have. We have talked about like properly modeling the human's psychological and basically like the human factor for learning. As some of previous talks covers, we need to maximize engagement and try to like deal with the limited capacity of learners' perception, right? And that limited capacity not only applies to explanations, but also applies to the intrinsic memory issue of the learner. And what we haven't covered, like for many other challenging aspects of human learning's aspect, is, for example, they might have limited inference power. Like if we ask them to generalize the concept, it may not be as easy as remembering a concept. There may be a mismatch between the model and the actual model learner is using. And sometimes we may call for more interpretable teaching interactions, so that we need to properly define the teaching interface so we can interact with the learners more effectively. And if we imagine teaching human learner to learn some physical task, there might be safety concerns and fairness concerns. So all those are like very exciting open problems, and I'm excited to hopefully work together with the community. All right, so I think I overrun for 1 minute, and if I have time, I'll just take questions. Otherwise, I'll be happy to chat offline.
Yeah, thank you. Thanks a lot for this very interesting talk, Yusin.
Thank you.
We have time for a few questions. And I saw that, Julien, you asked a question in the shared notes. So maybe I can try to unmute you to just let you ask your question yourself. Let me try that. Okay.
I think I'm unmuted now.
Ah, okay, yeah, that's good. Okay.
I can hear you.
Okay. No, I had one question about, but I think it is in your conclusion slide. It's about how do you tune HI, and if there, I didn't understand this, and then is there some uncertainty on this parameter, and does it affect the
Yes. Oh, okay. So the actual experiment we did is like we first thing we do is to just eyeball the forgetful curves in simulation. And so we try out a match rate of different parameters, and we test the system ourselves, and first make a rough call on whether the choice of the parameter makes sense to deploy to real learners. And then there is also, since we have this kind of interaction mechanism with the learners, we can adjust our parameters based on the real user's feedback. And so asking the user to make a guess itself is kind of a preference or model elicitation step.
So there is two learning steps. There is one with offline data and one with the sequence of the user. Like you first tune HI for many users, and then you adapt HI with the sequence of the learner.
So in ideal setting, yes, that is what we're hoping to do. But for the sake of experiment, we're trying out a match grade and just fix that parameter and deploy that to the real users. So there's no second step for the course of the project, but what you said makes sense, yes.
Okay, thank you.
Yeah, you're welcome.
Great. Also, I saw that, Arthur, you have also a question. Maybe you can try to unmute yourself and ask yourself the question if you want. If there is an issue, you can write it in the chat. Otherwise, I can just like read your question. Okay, I will. So I will move on. So the question from Arthur was, do we have any idea how much people hired through Mechanical Turk give realistic data? So he would expect that having motivations to learn German, for instance, yes, would improve a lot the performance of the learner.
Right, that's a great question. So for German, we have a total number of 100 different vocabulary words. The number of words we actually put into test is slightly less than that, but just roughly the same. For the biodiversity, if actually I unfortunately couldn't show the example data set, there are some very interesting species which is kind of amazing to learn from. In terms of the participation, so since it is a kind of standard user study where we do have some monetary like incentives for users to perform, and we based on the geographical region, we also do a filtering to make sure the learner is like legit learner that gives a reasonable responses. And we do, however, have a post-processing rule for plotting the curve, basically trying to look into the answering patterns. If the learner is obviously a random guesser, then we just filter it out. but we're not freeing out too many users of this kind. To summarize the question, the answer, we do have a pre-filtering on who can participate, and post-processing like filtering out obviously random patterns. Thanks for the question.
Okay, so I think that all questions have been all questions from the chat have been asked, and I have also quite a few questions myself, because so personally I've been working on your paper. Oh, so here's Arthur. You want to ask the question or to elaborate on that? Oh, I see that you are muted now.
Yes.
Okay, so maybe so yeah, as I was saying, I have been working on extending your greedy algorithm, and I'd be happy to talk to you about this and Oishin later on. But so I had a few questions, and for instance, so I've been asking myself, your reward function is compensatory across time, right? Because you can compensate future sharp decrease, for instance, with initial very high correctness probability. And in fact, it could be possible that we want not just like very short-term high correctness probability, but something less sharp and more more flat across time. And this is because of the additive form, right? And have you thought of alternative reward formulations? And maybe I was thinking of sorry, it's difficult for me to say, regularization on the mean memory decay rates. This was some just random thoughts.
So can you maybe briefly elaborate what would you mean by sharp increase? Like,
yeah,
different concept.
Yeah, I mean, if you have very in the initial timestamps of the retention period, right? You may observe very high correctness probability, but then if let's imagine that the strategy that you implemented just yielded very high initial correctness probability, but then the memory decays a lot very rapidly. And this is not something that we want, right? We want something more flat. We want the decay rate to be more, and have you thought of alternative reward formulations that would take this into account and that would prevent the compensation between timestamps and between short and longer term retention?
Right. Okay. Interesting. I think very interesting point. I think the objective somehow is like considering that, maybe not to the extent that it give you a good behaving performance algorithm, because if it is a very sharp retention rate decay, then that is a very easy concept, right? So if you want to, like, say, get a potentially promising practical algorithm out of it, we could do grouping of the words based on the difficulty level. And then maybe assign different weight to different groups of caliber words, which is kind of what we were trying to do when we do the biodiversity experiments. We have like common words and uncommon words, which is more difficult. We actually look into different groups of words separately. But a more soft approach to do it is to maybe weigh the contribution to the objective, like according to some soft weighting mechanism. But I think in terms of the theoretical guarantee, it would be very interesting to see how that affects the analysis. Great question.
Okay. And so for a final question, so I've read the papers from the adaptive spacing literature, and some papers try to implement reinforcement learning based algorithms. For example, there is this paper from Reddy et al. At a workshop in Europe a few years ago, I guess. And so I was thinking, would you expect your own greedy algorithm to perform better or worse than these types of DRL algorithms? Because yeah, RL would take the whole sequence into account, right? Not just the expected consequences of the next item choice.
Right. Yes, great. I think that's depend on what kind of memory model. If we use like if the learner's model is dynamic, then we can't say much about the performance. We do have a theory like theory 1 and theory 2 I show in the slide is applying to general learner's model, assuming that there's no mismatch between the teacher's estimation and the learner's true model. But if we need to approximate learner's model over the course of learning, then there's obviously a model mismatch. The bounds does not hold anymore. In that case, I'm not sure if using a wrong model and use the greedy algorithm based on that will outperform the a better match the learner model estimation. So yeah, answer is perhaps not, but it'll be interesting to see how the analysis pans out for this line fork. That's also a great point.
Oh, okay, great. So yeah, we can talk about this later, because I've done some experiments around that also. Okay, perfect. So great. Thanks a lot, Yusin, for this great talk. Now we are going to move on to the next talk, which will be presented by Fu-Hua Lin. So Fu-Hua Lin is from Athabasca University in Canada, and he will tackle the topic of adaptive assessments on a gamified e-learning platform with his presentation on the subject of adaptive quiz generation using Thompson sampling. If Fu-Hua, you're here. So I'll let you start.
Yeah, thank you, Bennett. This is Oscar Lin, and yeah, my former name is Fu-Hua Lin. But people call me Oscar. That's for easy pronunciation. I'm a professor of Athabasca University in Canada. Thank you for giving me the opportunity to present my research on adaptive quiz generation using Thompson sampling at the WASL 2020. Okay. I will start my talk with a brief introduction and then the literature review, and then present the idea about how to model the quiz generation process as a better Bernoulli banded model, and then solve it with Thompson sampling. The last part is conclusion and future work. Formative assessment has been proposed to make education more effective through identifying and closing learning gaps. Specifically, this intent to generate feedback on performance to improve and accelerate competency acquisition. So there are three principles of formative assessment. First, the formal assessment should be viewed as an integral part of instruction, usually in real time for guiding learning process. And second is formative assessment fosters student involvement. That means the student should not be punished for their mistakes. Instead, they can use assessment for self-guidance and to monitor their progress towards learning objective. And the third is a formative assessment requires constructive feedback to close in the learning gaps. In face-to-face teaching environment in campus-based university, face-to-face tutoring and classroom discussion has been used for formative assessment. But this is not possible like my university, online university. As you may know, Athabasca University is almost fully online university. We already have 50 years since 1970. So this year is 50 years birthday for our university. So now during the pandemic, the enrollment now is still very increasing. Yeah. So that's it. So formative assessment, they're like face-to-face tutoring and then classroom discussion is impossible. So that's why now learning analytics and educational data mining explore how data generated by students can be used, can be analyzed or utilized to drive online learning system to offer adaptive learning. So in assessment, we talk about adaptive learning is we mean adaptive assessment. In adaptive assessment, the goal is to optimize the computerized assessment process so the student can receive accurate evaluation in as little time as possible. Traditional adaptive assessment is based on two approaches. One is called IRT, item response theory. Another one is called error rating. Both are used widely, but they have some limitations. First is the complexity in implementation. The second one is the premise that the different questions measure one common trait. So in this research, we try to design an algorithm that can accurately and quickly identify the learning, the lacking areas of knowledge of the student. So we model it as a better Bernoulli-Bennett model, and then we use a Thompson sampling, one of the multi-arm bandit algorithm that can use prior knowledge. So multi-arm bandit algorithm are named as after the problem for a gambler who must decide which arm of a case law machine to pull to maximize his or her total rewards in a series of trials. They are capable of negotiating exploration and exploitation trade-off. They have been applied in real-world applications solving optimization problems such as website optimization, clinical trials, experimental design. Okay, in formative assessment, WASL and Nowicki proposed a adaptive testing approach method based on upper confidence bound, which is simple and offering a sublinear regret and non-random, and using for smart exploration. But the drawback we found is the UCB, upper confidence bound, cannot use prior knowledge. Why the prior knowledge will be very helpful and will be available in most cases to enhance the performance. Okay. So to model the quiz generation process, we map the gambler to the assessment system, and we map the learning objective, or you can call knowledge component in some cases. But in assessment, we prefer learning objective. So if we map a learning objective to arm, in the multi-unbounded model. And reward is replaced by answer, the answer by student, so 0 or 1. And the goal is to explore the different topics and engage in focused questioning, exploiting those which are possibly in most need of further learning or remediation. So the Thompson sampling approach was proposed by William Thompson in 1933, long ago, and has been used in simulation and real-world applications. It is a smart, smarter exploration rather than greedy and random. So the main idea is to use by using the approach to estimate the rewards and randomly select an arm according to the probability that is optimal. So here we first model the process as a better Bernoulli bandit problem, and then solve use Thompson sampling. So there's several basic models to support our algorithm. First, called domain model. The domain model consists of a list of knowledge unit in a course, and then for each knowledge unit has a list of learning objective or knowledge model, rather knowledge component. Sorry. And for each learning objective, we design and store a set of questions. So each question is tagged with some features, including like correspondence, knowledge unit on the learning objectives, and the feedback. So these are the very basic model for in adaptive learning people used, but we use here. And for the student model, for learner model, it's represented as a time series matrix at the different level. So there's 3 levels. At the top level is called knowledge unit level, and second is called learning objective level. So the value is the probability that the student can answer the questions of a learning objective correctly. And then at the question level, we call all the answers by student. So in Bernoulli bandit model, there's a K actions. And when played at the time t, action produce a reward with success probabilities, we call theta k. So these probabilities are known and fixed over time, and so therefore can be learned. So the goal is to maximize the cumulative number of successes over t periods. So now let's see how the model deploys the quiz sequence generation. Given a set of learning objectives, we begin with independent prior belief over each theta k, and then take these priors to be better distributed with the parameters alpha and beta. And alpha beta corresponds to the counts when we successed or failed in learning objectives to get a reward respectively. And then we can calculate the prior probability density function of the mu k. The optimal policy is to choose a question which the learning objective for which MuK attains its smallest value. Then based on the Bernoulli bandit model, we adopt Thompson sampling to solve the problem. So basic idea is to randomly sample the success probability estimate. We use mu hat k from the posterior distribution, which is a better distribution with parameters alpha k and beta k. So the next step is to select and apply an action according to the optimal policy, and then update the posterior distribution of the selected action. Now we are using my team. Now using JavaScript and Python, MongoDB to develop a formative assessment system to do the experiments. The integrated with a learning management system model. We organize the system for course as several stages according to the unit. So each of them corresponds to a knowledge unit, and then we use now we use a data structure and algorithm course. I am teaching as the first online course, and then we are going to use English course, language course to test the algorithm. So now at least more than 120 students, undergrad students of my university, will participate in the test. But now, yeah, unfortunately, we don't have a testing result yet, experimental result yet. So for the future work, a lot of work, yeah. And we are still at the initial stage. It's a lot of work for developing, deploying, and testing to do experiment. So we feel Thompson sampling should will work better than UCB because it's a Bayesian approach and can use prior knowledge, can use student model. And so we're going to measure the performance of the algorithm we call benchmarking. One of the approaches we can use is as a positive predictive value. Maybe we explore other index to measure the performance of the machine learning algorithm. So, okay, thank you. And also I would like to take this opportunity to thank the reviewers for your constructive comments, feedbacks, very helpful. Thank you. I'm done.
Thanks a lot, Oscar, for this very interesting talk. So I've seen that on the share notes, Julien has 2 questions to ask. So maybe Julien, you can take the mic.
Okay, so thank you for the presentation. I just would like to ask first, how many questions does each student answer during the test during the experiment you carried?
Sorry, Oscar, you can unmute yourself again.
Okay, sorry, yeah, I was muted. Yeah, we're going to use one quiz. We plan 20 questions for one unit, one quiz. Yeah.
Okay,
right.
Yeah. So it's 20 questions, and you have like 10. You have how many arms do you have? I mean, how many actions do you use?
Okay. Yeah. For each unit now. there are different number of arms, but from 3 to 8. Yeah, the minimum 3 and maximum 8.
And I have a question. Do you have it's my second question. Do you have do you use some prior knowledge? I mean, with the Thomson sampling, do you initialize the prior, or do you use like an informative prior, like just? I mean, like, yeah. Do you do something with the prior just to, because since you have few data, maybe if you could use some prior, learn on other students. I don't know.
Yeah, so at the very beginning, prior, we don't have prior, we can use assume they are just a normal distribution. But later when the student play again and again, so they will use their prior.
Okay.
Yeah.
But you could use you could learn from the other student prior. Do you see what I mean? Or like you could use, because since it's a very short sequence. If you start with no prior at all, it will take a long time to learn something. So if you can use the answer of the other student to start with, maybe it could be faster to learn. I don't know.
Yeah, very good question. As you say, that's for the multi-arm bandit. The very important parameters is the length of the horizontal. So that's we were still we may change. We use the length as a parameter to compare what how long should be better for quiz. Yeah.
Yes. Okay. Thank you.
Okay, so I see that another person is writing in the shared notes, but I don't know who is for now. So I will. Oh, it's Hiroshi. Okay, Hiroshi, you can unmute yourself if you want, and ask yourself your question. Okay, so if
sorry, I haven't hear the question.
Yeah, I think he has troubles with the platform. So maybe I will start by asking myself the question he has wrote. So does Thomson sampling assume constant mu I? So the mu I is the reward of the arms, I guess. Yeah. And in the adaptive quiz case, so Hiroshi thinks the mu I's are changing, and does it affect the algorithm? So maybe you could go back to the algorithm pseudocode so that we can see what we are talking about. Yeah, thanks. I think this is it.
Yes, you are right. Yeah, a very good question. This mu I, they could be changing, over time. But for the current quiz, for foreign quiz, we assume they are fixed. So, but they are non-stationary. As you said. But for the when there's still have a question about how to model this the mu. Yeah. So when students learn and the mu k could be changed. Yeah.
Okay. Thank you. So I had another question myself. So I'm thinking about the user experience, and I was thinking, don't you feel that the students would get frustrated rather than engage because the goal of the algorithm is to find the weakest learning objectives. So you will try to make them fail each time, right? Or at least this is what will happen. Don't you fear that they could get frustrated? And would you, for example, plug sometimes some random items to make the experience more enjoying?
Yeah. Excellent question. Is that this is so we have a game-based system called Quiz Master, and we have been developing and using. So the Quiz Master is game, so that's for fun, and so that's engaging is an important consideration. But now we are talking about optimization. So we will consider several objectives. So one of the objectives should be identify the weakest areas. So then we can consider the second factor about the fun game factor, fun factor. So how to combine together in a gamified system. That's another topic we're going to explore. That's about game design. So, but from the pedagogical point of view, a very important thing is to identify the weakest lacking area. Thank you.
Okay, and so maybe we can go to our final question now, because I don't see other questions. And I have one final question myself. And so it's why have you had preferred multi-arm bandits methods rather than other types of methods such as using, for example, the Fisher information with a student model such as IRT or stuff, and why using especially MAB algorithms?
Yeah, the main reason is that we have been try to model the level of difficulty for each question, but that's most difficulty tag. And so we find it's very difficult to maintain the question bank, because the level of difficulty is so it's a relative. It's a relative feature. I mean, so the different student, for one student they feel difficulty, but for another student maybe not a difficulty. So that's the main reason for we feel it's hard. It's harder to use IRT. And another one is the IRT has all the questions only match one common trait. So, but here there's a multiple trait to be measured.
Okay. Maybe JJ would like to talk to you about this later with you, because he has himself developed an algorithm for a student model which takes multiple traits at the same time. But we'll see that later. Okay, so if I'm not mistaken, we are at the end of the question session and at the end of our second talk session. So maybe we can take now a 15-minute break. So we'll be back around 5:50 European time, so in 15 minutes, and for the open discussion. And yeah, so see you everyone in 15 minutes. And thanks a lot again, Oscar.
Thank you very much. Yeah, I think we can even meet again at 5:05, something like this, or
5:05 European time again. Okay.
Yes.
Okay. Good. So in 10 minutes, right?
Yes.
Okay. See you.
Hi again.
Hi.
So we can, I think we can start. Yes, we can. Oscar, we hear some echo from you.
Oh,
If you could put headphones or earphones.
okay.
Yes. So I suggest we try to open our webcams until no one can hear each other, and in which case we will switch back to audio only.
Everyone who wants, of course.
Yes.
I don't know if this is it still broadcasted on YouTube, JJ?
Yes, it does.
Okay.
We can.
Okay.
It says to me webcam sharing is not activated, so is verrouillé, locked.
Yeah, that's true as well. But so that's yeah. I will open this. I will give every access. But it's fine if you just keep your mic. And so thank you so much for staying up to the open discussion, and thank you for the great talk. So let's hope that now that we have in mind everything that was said, we can still discuss about how collaborations can continue and so on, and what are the different difficulties that we have. And so if as a start, like I feel we could start with the fact that it's a bit hard to know what kind of data we have access to, and what kind of data we need in order to go further in this optimizing human learning community. So for example, indeed, like there are some data sets like assessments where you have that are collected on many users answering many questions, and for which you observe all attempts. But sometimes you more like have data like of Anki, where it's more like private data, where you know everything, all the successful outcomes you got, but you don't have data from other students. But still, you could still calibrate some student models in order to know what is your own performance. And the question is what can we do in order to what is the kind of data that is needed, and how can we optimize models with the one we have?
Now, yeah, in my university, we need to submit a proposal called research ethical tool from a board. Then we can record, we can log student data, and then use in Moodle.
So Ushin here. Yes. So JJ, to expand on your question, do you think is data alone sufficient, or do we actually really need like some kind of sandbox where we can do interactive experiments, efficiently, easily, cheaply, with ideally real people, or something close to approximating the complexity of real people?
Yeah, indeed. Like all these things take a lot of, like, if you're making another platform, right, in order to try new things with real people, that would be the graal. But what I enjoyed in your talk is that you showed that indeed, like, even if I just have my private data, my private data of me annotating birds, let's say, actually a machine learning algorithm can help me be better at that, even if it's just me with the machine, right? So this is what you showed. You don't need the data from other students.
Yeah, no, that's a good point. I mean, in practice, the world of this kind of teaching problems is really long-tailed. There's many different tasks that many different people want to learn, and in practice, it might be hard to expect that we can find With the exception of some tasks, there's not many that truly have like, hundreds and thousands of people that we could work with. But I guess I mean this, I think your answers really make sense, and I'm thinking of it more from like evaluation point of view. So I think when we want to deploy these things and let people use them, I think it definitely makes sense that we just let people run with it on their own. But if we want to like at scale, evaluate these models, compare them fairly, etc., that for me is a big bottleneck at the moment.
Yeah. Okay. So, but yeah, like so. Indeed, in order to evaluate, you need so you would need this the training your adaptive algorithm with people like what Usha showed on a mechanical Turk or something. But or you actually showed you made your own platform, Oishin. But I hope that we can still do some nice stuff with offline data. So sometimes you have data that was already collected according to some policy. But if this policy allows to take some random, it's not like strictly enforced. If your policy is moving enough, I feel you can still try to refine your policy to see if it can be improved. But just in the case if it's exploring enough. I'm not sure I'm making super clear.
I agree with you. It's a very pragmatic solution, I think, to the problem. Yeah, so I agree with that in part.
Right. So this is Usha speaking. If you can hear me, there are actually dedicated apps, right, for like this teaching vocabulary of words. We have like Duolingo Memrise, and for also a existing body of platforms for the MOOC interface, like Coursera, like Udacity, Canvas, for example. So those are designed for different purposes. Sometimes they just want to teach people to memorize things. Sometimes to teach people to learn different tasks, as we can see in a series of talks as well. So like one clarification I want to raise here, like what is the scale of teaching? Or trying to teach, like how complicated a task we're trying to teach, and maybe we'll have to design different tools either to gamify that particular teaching session, or maybe simple tools to collect data from the crowd.
Yeah, that's true.
Maybe that's a question direct to JJ or anyone else who are like the difficulty level of the task. Like what task are you imagining that want to model, like learning math, for example, or just learning machine learning, like teaching a machine learning model, or teaching concepts that is just repetitive?
So in the case, I was mainly referring to like let's say math or anything that can be mapped with skills, like one or multiple skills. So everything that we try to mention. But like I don't know if so Arthur wants to, like Arthur has some experience in Anki, the Anki platform and the different algorithms that are plugged in, or the kind of data. But for example, Arthur, you were telling me that it's usually hard to know what is the skill information that is at a higher level than the items that people are usually
trying
to memorize.
Hear me well, so if so, I will explain.
Yes.
Okay, great. Hi, nice to meet you. So I'm first I should state that this is done personally and not related at all to my work, that my employer asked me to state that it's not related to my current job. Okay, now that it's done, I am the maintainer of Anki. I'm actually one of the 3 active maintainers and contributor to Anki and a user of Anki. This means that I have some experience with spaced repetition software, since Anki has 1.6 million users currently, active users, not only downloads. And I created a way to plug a scheduling algorithm into Anki. I shared the link with Jill-Jênn and could share it later, which means that if at some point you want to test algorithm with real users, it could be easy to plug it in Enki and let people just try it. Of course, these technical details that need to be solved, and this means that you can only use one personal user's data, and that you can only use what is logged in Enki's database, but that's still something that is possible. And there is a small but active community of people caring a lot about scheduler and wanting to improve it. So I have no worries that if you just come and say, hey, I have a scheduler, I want people to try it, you can try it. Okay, and for information, Enki term of service allows the Enki company, Enkitex, to share data anonymized and like to share log of review, but not the actual card content, with academic. So if you come to them, is allowed, I don't know if you will do it, but he is allowed to share log of review. So that's something also that seems to be useful, and don't hesitate to come to me to help to interface with Enki. So now to answer what was said precisely regarding mathematics, what I found to be quite useful as a user this time is that, let's say you want to learn complex notions. I'm going to use a really simple example, geometry. Let's say you want to learn that a square is a diamond, which is also a rectangle. Then you need to learn what a rectangle is. It's a parallelogram with a right angle. Okay, so you need to learn what a parallelogram is. A parallelogram is a trapezoidal with two opposite sides, two pairs of opposite side of same length, and so on and so on. When I want to learn something complex such as category theory or graph theory, I realize that there is such a deep volume of, there's so much deep depth in the set of things that I need to know, that my problem is not to learn definition, because all of the definitions in the first chapters of category theory is really easy. The problem is to learn definitions which use other definitions which were samples, but that I do not already know correctly. So Enki has helped me a lot to learn the simpler definition, and then the definitions which use the simple definition, which are simple by themselves if I know the previous definition. And so I'm not saying that it's going to help me do research in mathematics. I tried and that was not really successful, but it's really helpful to learn complex concepts when there's some depth and some knowledge is using other knowledge that I learned in the past. But that means that I need to have a correct order in which I review the cards, because I need to ensure that if I learn a new card, I have already learned the prerequisite before. So I did it partially. It's not really well done, but that's something that can be done with Enki currently.
Okay, thanks a lot, Arthur. And so I was thinking about what you said. And yeah, when you say you learn mathematical concepts, is it how to apply those concepts, or the definition? For example, you were talking about the definition of rectangles and stuff. And do you mean knowing when to apply which rule, which mathematical rule, or which mathematical process, or knowing just the raw definition of the concept?
I'm actually learning quite a lot of different things. So I'm learning definitions. That's really the simplest example. When I'm learning sometimes theorems, and so what are the prerequisites of the theorem and what is a counterexample, which means like if one of the prerequisites is broken, explain why the theorem doesn't work. So for example, if you require property A, B, and C to imply D, give an example of something which satisfies property A and B, but does not satisfy D because of C is lacking. That seems to be, that my experience is really useful to understand that concept. I've never really tried to do anything which is related to applying mathematics. I've mostly been doing theoretical mathematics before. So I have no experience in this particular field. The closest I had would be with programming, which is clearly applied, but like it's usually quite simpler, such that I'm learning that I have cards which helps me to learn that if I want to access the keys of the element in the dictionary in Python, or the pair of key and values, or the set of values, which method should I use? And that's not really something complex, but that's something that I kept searching on Google before. And so it's making me win some time when I want to apply my knowledge to real life stuff. I also use it to learn music pieces, which is applied in a sense. I don't know if it really answers your question.
Yeah, I was more thinking. Yeah, I think this answers my question. And okay, I have another question for you. Yeah, you said you must ensure that the prerequisite has been mastered before going on to later concepts. But how do you assess that your concept has been correctly mastered? You have something like the Lightener system where when the card reaches the final box, then just like goes away, or do you have some kind of probability that the concept has been mastered, such as in Bayesian knowledge tracing? Or
yeah, this is going to be even simpler and not really good, but like in Anki, a card has what is called an interval. That is, how much time are you going to wait before the previous review and the next review? We usually state that a card is mature if the interval is 3 weeks. A card is never going away except if you choose to delete it or suspend it. And so what I can do, which I can theoretically can do now, but I've not really done a lot because it's going to take a lot of time just to manually enter the dependence between each card, is to state that I'm going to state that I know the content of a card if it is mature. That is, if I can spend 3 weeks without needing to review it and probably not forgetting it. That's something really simple, and since you were speaking of application, it only states that I am able to recall the definition, but know that I've really understood the concept. So, but all the time with Anki anyway, I'm the one which is going to judge if I know or don't know something. One of the problems with this, so as I say, is that creating a data set is going to take a lot of time because you should do it manually and enter the dependencies. And the other problem which we have in the Anki community right now, which is really the biggest problem, and that was related to, is that for copyright reason, there's really little things that we can do, because even if we want to reuse a text or from a textbook, an image from a textbook or from the search engine, we are going to have copyright issues. So we can do it on our own collection, but we cannot share it legally. Decks are shared, let's not really legally by two friends. I can send something to a friend and that's okay. But I believe that one of our biggest problem right now is deck sharing legally, because there's really huge limit on what we can do. And until there's a way to create something and really collaborate together in safe way, we are quite limited, and most of the time people do their own deck, except for very simple things such as foreign language, where, well, this is no real question of copyright of a dictionary.
Yeah, that's a strong point, this kind of like copyright issues. So I would like to go back about the to put an idea here, and the fact that indeed, like the Oishin's talk about the fact of directly trying to find relevant features that can be good, like visual explanations of items in order to that are related with utility. Do you think it would be possible to, because I feel it would be, let's say we had a lot of math data, like let's say additions or multiplication, and the relevant feature that would help explain why a particular calculation is correct or not would be the fact that so you could map the difficulty. You could make a mapping between the difficulty of an item and the feature. So which means some exercises are harder than others because they require more skills to be solved, but this could be identified automatically. Okay, so this is how we could extend this kind of idea to other domains. But the question is now becomes, could we generate an exercise directly like so that are at the right level, right? You could make some interpolation, which means now in my data set, I have many items of different difficulties, but now I want one difficulty that is slightly in the middle in order to get some personalized and personalized item bank.
I mean, if you take the really question of addition, I think that's the example you gave. Yeah, I guess that I could take into account the easiness, the log review or the interval, and generate and ask each time questions which are more and more difficult. So add 2-digit number or 4-digit numbers, but that's really because of questions that could be quite easily generated in JavaScript, which is a programming language behind the question and answers, and that it can access to the data. If we were going to speak of real mathematics, for university level mathematics, I don't really see how you could do it, because I don't even see how you would generate a lot of questions.
Yeah, JD, when you were talking about generating questions, was it generating from scratch, or I mean generating questions that have not been already implemented in the database, or such as templates?
I was thinking about from scratch, automatically from scratch.
Yeah. Okay.
I mean, in this case, it's not a question of space repetition software. It's a question of how to generate good mathematical questions. And I have no insight here.
I think that JJ, I don't know. I'm not sure if I read this or just imagine it, but I think that I read a paper on generating the correct images with the help of deep neural networks. So basically the task was to recognize different categories, visual categories, but I think they were just completely made up, not real categories such as butterflies. And so the idea was to teach students or human learners by providing them the images. And so in this case, they were able to automatically generate the best examples to show the students. And if I remember correctly, the researchers found that the algorithm was able to reproduce some kind of fading, blocking strategy from the cognitive science literature. So a difficulty that was increasing at the right pace, and blocking, which means putting some chunks of the same category next to each other. And but I think it would be more difficult for something like math. I don't know.
Maybe this is not what JJ was talking about, but it did make me think of something, which was that one way to generate these explanations is obviously to get learners to provide them as they go along. So in some sense, having learners provide explanations is another mechanism to enforce them to learn. And learners of different skill levels will provide explanations of different degrees of difficulty, maybe related to different concepts in the data. And so it gives you this nice mechanism to both evaluate people, but also to generate newer instructional material through interaction. And I guess that applies to the mathematic example. Like people, again, at whatever their skill level is, they should be able to generate new questions appropriate for other people at some lesser skill level. I
was feeling that as so to to clarify what I was saying, I was feeling that what you managed to do with a really high dimensional content such as images, we could also do it for slightly simpler content, like in mathematics, like the range of what you can do with exercises is quite lower. So that's why I was feeling it could be also applied to this kind of item generation. But indeed, in your case, when you ask humans to provide explanations, you're both improving themselves because they have to explain, to justify why this bird is this bird, but they can also improve the classifier, the machine classifier.
So one other thing that related to what Arthur said that made me think was, like, could we envisage, and this is a bit out there, but could we envisage like a marketplace for these algorithms, in the sense that, you know, we have a platform like whatever flashcard platform you want to look at, and basically in a competition sense, people could submit different algorithms, and ones that kind of rise to the top of this pool would somehow be deployed with real people, and we'd have efficient mechanisms for kind of deciding quickly if a given algorithm was not particularly useful. And so in that sense, we'd have this continual evaluation pipeline. Okay, this would be the dream, but we'd have this continual evaluation pipeline that whenever you come up with a better algorithm, you submit it to this pool, and hopefully if it is truly better, it kind of rises to the top because it gets used more, because it's more effective, etc.
I was actually thinking and beginning discussing with Anki community about the fact that there could be a public API for schedulers. There are two problems. There are people providing their own schedulers, and so they just take the database and change it and give the database back, which is not really practical. Creating such an API would really not be complex. The first problem would be that, I mean, you are quite restricted by the log. So for example, if we consider Anki, which I'm going to consider because that's the one I know the best, it's not really clear how much you can adapt it to anything which is not Anki, because in Anki you have an option of cards. You have a fixed question and a fixed answer. So you can put JavaScript in the question and answer to adapt it and change the question from one time to another, but that's really a small thing. And so if, for example, like Duolingo, you want to have grammar notions, which is related to multiple cards, or if you want to have link between cards, that things that cannot be given to one specific API. So I don't see today how to make an API which would allow to generalize as much as we want and to use all of the concepts you have discussed of today, and that may be used by, for example, super memo. And at the same time, that would be, I mean, each application has a different set of data and relation between questions and answers, and having one really general API for all of them seems quite complex. Having an API just for Anki and the way it is now and its saved data is something that I can probably do in 1 weekend or two without trouble. And in the Anki community, there are, as I say, people really interested in having better schedulers. I'm pretty sure it would not be a problem to find a few dozen people willing to try new schedulers to see if it's better or not, as long as they're able to switch back to the previous schedulers and not lose anything if there's any trouble, which is not a problem by itself. I can deal with that. It's really not a trouble, but I cannot promise. Like, even if there are a million of users, most of them do not care so much about the scheduler. And so it's going to be hard to really ask them to have a really huge number of people to switch.
Oisin, regarding your marketplace, how were you considering evaluation? Which means, like, you would download an algorithm and people would provide some feedback about their data. given an algorithm, right? Like,
yeah, and I didn't want to use marketplace in the sense that there was like a monetary value associated with it. I meant just more like it was a kind of a competition pool in some sense of algorithm. But yeah, so
I see.
what would the metrics be? So in the ideal world, we would just like A/B test all these algorithms on people, and they wouldn't even know which one they were using. And then the people, I guess, in some sense that were performing better, whatever that metric might be overall, given a given algorithm, would be we would attribute that to the algorithm itself. So again, if we had enough people for each of the algorithms, we could then do some kind of estimate of their utility.
Yes, and actually, this is something that it's a luxury that people like Duolingo can make, but not so much us. And actually, some other companies don't even want to give up their A/B testing because they are too much afraid to lose money or customers or something.
Yeah,
So,
no, that's why we would have to be careful that you'd you'd have to have some mechanism by which any new algorithm wouldn't just automatically be deployed on people, because it might actually be detrimental to their performance. And we'd have to have some mechanism, maybe through simulation, first evaluating them, and then they get to be promoted to small numbers of users and then large numbers of users, etc.
Yeah, in fact, in the Linset old paper, so they were testing an adaptive spacing algorithm on the real-world students, and the thing is, they were comparing to a fixed schedule and a generic schedule, and on real-world students. And so what they did is that they had some kind of within subject experimental design. And which so every student had every type of recommender system, so that and so in the end each vocabulary word was weighted in the same way in the final test. So that way they could prevent students from being harmed by a bad recommender system actually. And so this is something that could be potentially used to give every spacing or every algorithm to every student, but on different parts of the knowledge domain, so that it's not that detrimental. It's not detrimental to people because everyone will have the same, but on different pieces of knowledge.
Yeah, that makes a lot of sense. Yeah, that's a good idea. Yeah.
But this is sometimes difficult to implement. For example, when you have relationships between the different items, and so I don't know how you would do that, because it would be difficult to cut this kind of graph in a good way. But I think this could be a good, interesting way to circumvent that.
And I think Arthur's point is very valid, this idea that, there's only so much you can do with flashcards, but I think that that's still a very interesting space and still affords a lot of interesting questions that can be asked. So it wouldn't bother me so much that only allows us to explore one type of teaching paradigm interaction. I think that, if we can succeed there, obviously we can move on to more challenging things afterwards.
I feel in some systems, I'm again taking the example of Anki, like the fact that you have the ability to download many items and so on. I feel it would be nice to have some statistical utility, statistics about usage, about these exercise, in order to know whether they are too difficult and so on, so that you could improve your local scheduler. So I guess nowadays there is a need for this kind of tools that can still keep the privacy of your data in your own device, but that can still like send back to server some aggregated data, so that you can share it with the community. So not only share the items, but also the machine learning weights, I guess.
Yeah, that makes a lot of sense. Yeah, you'd imagine any of these things should be opt-in, but that seems like a smart way to get anonymized data as well.
So, okay, so I guess if anyone wants to ask anything, you can just raise your voice. But otherwise, yeah, Oishin? No, is there anything?
I had a question I discussed a little bit in the with Alison. Sorry if I don't know if I ought to pronounce your name, which was how do you create data set of images? That was really what I was wondering, because like if you need to teach bird, if you need to go and take a lot of pictures of birds yourself, because also in order to be sure to have the right. It seems that creating any cards any collection of things to learn is going to be extremely complex, extremely consuming time.
Yeah, I mean, that definitely makes sense. And I think in the context of certain domains, that's very true. You know, so if it's medicine, collecting those images will be hard. Having even access to them in the first place is hard. So the reason we focused on these kind of species identification tasks is because there readily is large collections of images available. So there's two sources that we work with. So, and I'll type them into the chat after this. So one of them is called iNaturalist, and this is a community science project where people upload basically literally on the orders of millions of images every year that they take out in the wild, and then people assign species IDs to them. And so that's one of them. And then the other one is eBird that I mentioned, so the Macaulay Library at Cornell. And again, it's another example where there's people who are fanatical about birds, and people will upload, again, literally millions of images of birds every year. So there we can easily pull from this set of images. We have active communities of people that really want to learn these tasks. So it's kind of like a really good proxy for some of these other visual identification tasks that you might have in medicine and etc.
Okay.
But your point is well taken, yeah.
Right, just to add on the flashcard points, I was just thinking you were asking for the teaching German example. So there we actually we're working with a professional German teacher in preparing like a very dedicated, easy to identify word. So that is, I think, to the other end of like a crowdsourcing platform. So we could do both ways, like for maybe more. It's kind of designing a curriculum like in a real world teaching scenario where we do need like nice materials. In a case where we don't have enough resources to such as iNaturalist for other like type of objects, we could afford to some extent human labor to collect the data, like high quality data.
I guess actually that what really surprised me the most here is that I've heard no discussions. I would have expected that it would be different to teach to people who want to learn and to teach to people who have to learn. Because, for example, if you have tell me that, okay, you are going to learn for high school baccalaureate the name of all countries and where they are on the maps, that would have sounded so boring to me that maybe I would have tried to do it, but I would not want to do it. And so I believe that it's something you have to teach ways, which is, I mean, spaced repetition or something like that is still useful, but that it should probably be used tools which are quite distinct from the ones than the one I would use to learn some things that I want to learn and that I have the motivation to go every day and practice and learn them. And that was why I was surprised by the discussion about mechanical turks. And I was wondering whether there's any question here of whether the research is done to teach people what they want to learn or to teach what they have to learn, and how much of difference it's supposed to make, because I would really be surprised if there's no difference here.
Right, I mean, so, sorry, go ahead, Usha.
No, you go ahead, please, Usha.
Oh, okay. So for, yeah, so I hear someone asking as well.
Okay, can you hear me? You could go on, Yusin. We'll go back to Mohammed right afterwards.
Right. Okay. So for the just to comment on the mechanical Turk experiment. So that one we want to. So we do have a simulated model. And we have simulation results to show that the grid algorithm actually performing the optimal, right? We want to test out that just for the case of first fitting like the regression model to the real human user and see whether this algorithm actually works under this semi-real world scenario. Like we do have some curated teaching sessions, like over like 30 minutes, which is actually not exactly the same as real world teaching. But like if we care about interacting with a real human user, we can, for example, think about some gamified scenario where like users may get virtual coins if they learn some concept, even though they like to take away the need that they feel they're being forced to learn something. Like incentivize people, I think that's a very active thread of research as well, like how to do the mechanisms of design for teaching. So I think that's like very interesting research questions.
So Muhammad, you were wanted to ask something? Yeah, go on.
Yeah. So yeah, first of all, thank you for such a nice workshop. So I have a question for Banu that can you give me an example or anything else? So there is a learning system where we can use a student model or a without student model. I cannot quite catch you at that time.
Yeah, so basically you have multiple choices when you want to implement some type of adaptive algorithms for human learning. And for example, so just take this example that we had today. So we were talking about adaptive assessment, so how to converge to the right knowledge of the underlying knowledge state of the student in as few questions as possible. And for example, you can rely on a student model, which is a student which will model the behavior and the future performance of the student. For example, IRT, which is a basic student model. And then what you can do is basically take this student model and use it to formulate some predictions and be able to choose the best item that for the purpose that you have according to this student model. So this student model allows you to infer, to predict what will be the consequences of your next action. But on the other hand, other people, such as, for example, Oscar here, do not want to rely on such student models for various reasons. Here, because of the difficulty of the item difficulty calibration. And so what they do is that instead they do not assume an underlying student model. I mean, it's implicit. And they just define a reward function. The reward function is here linked to the weakest learning objective. And they just try to optimize this reward function. And they do not rely on a student model explicitly. I don't know if yeah.
Yeah, as in a link, you reference to a ITS MAB paper of like Pelmet and Ria, and you also mentioned some paper like Shayan Drudi papers, what is the reward? So if we see that, if we first discuss with the ITS under the MAB scope, they also use the same techniques which we used under the student modeling. At the backend, they also use the probabilistic, some weight and uniform distributions to get the student ability and then check the previous and current ability and then make a reward, which is called a progress of the student. And the similar process we do with the cognitive science, which you call as a student model. So that is why I'm a bit confused at what is the main difference between these two. We have a model and we have no model, but at the back end we are doing same things.
Yeah, not exactly. For example, I can send you another example in the chat. I just will be looking for it. It's an example of adaptive spacing algorithm. So it's to schedule the flashcards, and I just need to remember the name. Okay, I have it. And so it's based on deep reinforcement learning. Okay, and so their algorithm does not assumes an underlying student model. It's here. Okay, if you can see that. So, for example, here, so this one may be a bit confusing because they talk about student models, but they talk about it because they use it to simulate student trajectories. But in the end, the algorithm does not model explicitly the student's progress, for instance. I'm not sure if I'm clear.
Okay, so the main thing is that if we assess the ability of the student by using some cognitive processes, then it is called a simple student model. So if we use some different techniques like a bandit to optimize student by ongoing learning, then it is called a learning system without a student model. I'm right?
I'm not sure if this distinction is exact. Maybe can you rephrase a bit what you said, please?
Yeah, I'm said that if we use the cognitive processes or item response or something like that to assess the student ability on the base of some data and then recommend something like that. So it is called a student modeling. So in a learning system, so if we do ongoing learning using some other process like a bandit, so that is called a learning system without a student modeling. So I am right?
I mean, just like maybe the best definition is the simplest. Is just like if you have a student model, it's model based, and if you don't have, it's model free. Because, for example, there are multi-arm bandits who use student models to make recommendations. It's called contextual multi-arm bandits. And so it just depends whether you explicitly model the student performance or not. If not, it's model free.
Oh.
So by the way, like,
yeah, Jill-Jênn, you want to say? Sorry,
yeah.
Go on, Mohammed.
So if we, as we discussed that towards a model or model free, so if we see that MAB, so within a single state, MAB behave like a MDP. And if it behave like a MDP, then we can use a model free algorithm from RL. So why we call it that we did not need a student model here? It also behave like.
So yeah, but maybe like I would like to ask Yushin, by the way, the fact that like Yushin, in your system, you want to optimize the recall curve, right, over time.
Yeah.
So
yes.
This approximation, and so your model, so your technique is focused on this reward function. And my question is like, do you need to know the student model, and do you need some assumptions over the underlying student models?
Yes, absolutely yes. So we need to, if we want to calculate the future area under the curve for all the future recalls, we have to like hallucinate what the learner's behavior would be, right? If we don't show them, if we don't interact with them again. And their model mismatch is potentially very harmful to the performance of the system. Yeah. So that's why we're saying like we could estimate from the previous user preference elicitation or user evaluation from like other student bases. And for the sake of experiments, again, we're doing simulation. We're testing the system ourselves to basically find a parameter that makes sense via a grid of mesh parameter, like a mesh grid of parameters. Basically.
Yes. Okay.
Oh, right. Sorry. And then another thing is in Settle and Meter paper, the ECL 2016, they actually did the language experiments on a large user base just for the sake of estimating the parameters A and B for the half-lives. And we were basically built on top of that. We use that as a starting point and then see, try to tweak it in a local neighborhood to find the best parameter empirically.
Okay, I see. So this is a kind of an example a bit in between where you don't need to, I mean, you need to know the model, but the techniques, the algorithm doesn't, like can be applied no matter the model, and you keep the theoretical assumptions.
Yeah, it's agnostic.
Yes.
Yes. Okay. We do have a comment on YouTube, which is from 10 minutes ago. I don't think there should be one algorithm that works the best for everyone. I believe the algorithm should adapt to the user style and performance using all accumulated data. Then data from other users would be useful to predict performance for some users that don't have any individual data yet. So yeah, we do agree with you. So the question now relies in what kind of data can be shared or not. Benoit, do you, if there is anything, because I know that there are some people following us from Japan and Korea where it's like almost 1 a.m.
Oh, okay.
So,
oh, yeah. Yeah, if you want, we can just like end it in the open discussion now, if you think it's the right time.
Yeah. So thank you so much for the articles that were shared.
Yes.
All the papers and slides are on the website. So thank you very much, and thank you very much for all speakers again. And
yes.
Patch.
Thank you.
Yes.
Thank you, everyone.
And,
Take care.
Yeah, thank you for organizing the workshop.
Yes,
Thank you very much.
okay, thank you.
Yeah.
And feel free to reach out directly to the authors.
Yes.
Yeah.
And to the developers.
Yes, and thank you also, Arthur, for offering any help on the MK side.
Yes, thanks a lot.
Yeah. Thanks, Jill-Jênn, Benoit. Bye.
See you.
Bye-bye.
Bye. See you soon.
Bye.
Bye.